Please subscribe to support the channel. Could some stars actually be portals to other universes? It's a question that sounds like pure science fiction, yet it has quietly found its way into the conversations of some of the greatest scientific minds of the last century. At first glance, stars are nothing more than blazing spheres of plasma, cosmic furnaces born from the collapse of interstellar gas and dust. They live, they shine, they burn out, and eventually they die. But what if certain stars defy that simple life cycle? What if hidden within their blazing cores lies something far more extraordinary? Gateways that might connect us not only to distant corners of our own universe, but potentially to entirely different universes altogether. This isn't just idle speculation. It's rooted in physics theories that stretch back to Albert Einstein and the deepest mysteries of space-time itself. When we look at the night sky, every twinkling point of light seems remote, unreachable, and perfectly ordinary. Yet physics tells us that the universe is far stranger than what our eyes can perceive. The same equations that describe the behavior of stars, black holes, and gravity also leave open the possibility of wormholes, tunnels through space-time that could, in theory, connect one region of the cosmos to another. Some physicists have pushed this idea further, asking, what if stars could naturally give rise to such wormholes? Could the very things we rely on to mark constellations and guide human history be hiding entrances to realms beyond imagination? This concept isn't simply about finding shortcuts in space. It challenges the very foundation of what we consider reality. If certain stars could host wormhole cores, then the universe may be more interconnected than we realize. Stars would not just be cosmic light bulbs burning in the void, they would be cosmic gateways, natural constructs of space-time architecture that allow matter and perhaps even information to cross distances, or even cross into different dimensions. The possibility reshapes everything: our understanding of astrophysics, our view of the cosmos, and even humanity's place within it. And the intrigue deepens because science is not silent on this matter. While no confirmed wormhole stars have been observed, theoretical models suggest that such entities could exist. They could masquerade as black holes, appearing to astronomers as dark, collapsed remnants. Yet, if one looks closer, there may be subtle clues, radiation signatures, gravitational anomalies, or unexpected bursts of energy that hint at something beyond the ordinary laws of stellar evolution. So we return to the question: could some stars be far more than they seem? Could they serve as natural passageways to the unknown? The mystery is captivating not because it gives us immediate answers, but because it forces us to confront the vastness of possibility. Humanity has always looked to the stars for meaning, for navigation, for wonder. Perhaps, hidden among them, are doors we have yet to open, doors that could transform not only our understanding of space, but our understanding of existence itself. If we want to take the question seriously, could some stars actually be portals to other universes? Then we need to first understand what such a portal would actually mean. This is where the concept of the wormhole enters the stage. The term might feel familiar, almost cliché, because it has appeared in countless works of science fiction. From novels to blockbuster films, wormholes are often depicted as shimmering tunnels, glowing gateways through which spaceships zip across the cosmos. But behind the dramatic imagery lies a very real, very mathematical idea first proposed by Albert Einstein and Nathan Rosen in 1935. At its heart, a wormhole is a theoretical tunnel carved into the very structure of spacetime itself. Imagine spacetime not as an abstract void but as a kind of flexible fabric. If this fabric can bend under the influence of gravity, then in principle, it can also fold. Picture taking a sheet of paper, drawing two dots on opposite ends, and then folding the sheet so those dots overlap. Normally, to get from one dot to the other, you'd have to move across the entire sheet, tracing out the long path between them. But if you fold the sheet and poke a hole straight through, suddenly the 2 points are connected directly. That shortcut, that tunnel, is the simplest way to imagine what physicists call a wormhole. The math behind wormholes comes directly out of Einstein's theory of general relativity. This theory showed that gravity is not just a force pulling objects together but rather the curvature of spacetime caused by mass and energy. Under extreme conditions, that curvature can become so intense that it creates strange geometrical structures. One such solution of Einstein's equations describes what we now call the Einstein-Rosen bridge, a passageway that connects two separate regions of spacetime. In other words, the earliest wormhole model. But wormholes are not limited to just connecting different points in our universe. The equations leave open the possibility of even more dramatic connections, links to other universes altogether. That means a wormhole might not simply allow you to travel from one galaxy to another in a blink. It might let you step outside our universe entirely, emerging into a completely separate reality with its own laws of physics, its own galaxies, perhaps even its own versions of time and space. This possibility is one of the reasons wormholes have captivated physicists and storytellers alike. They suggest that the universe might be far bigger, more complex, and more interconnected than we can imagine. Of course, while the math works on paper, reality is less forgiving. Wormholes, as we currently understand them, are unstable. The moment matter tries to pass through, the tunnel would collapse, pinching shut before anything makes it to the other side. This is where exotic concepts like negative energy and exotic matter enter the discussion, ideas we will explore more deeply later. For now, what's important is that wormholes sit at the boundary of science fact and science speculation. They are not proven to exist, but they are not impossible either. They are consistent solutions within our best theory of gravity. So why connect wormholes to stars? The reasoning comes from the fact that stars and other compact cosmic objects are already the natural laboratories of extreme gravity. Black holes, neutron stars, supernova remnants, all of these are places where space-time bends to its breaking point. If wormholes are possible anywhere in the cosmos, these would be the likeliest candidates for where nature might hide them. And thus, the speculation arises. Maybe some of the objects we think are ordinary stars or black holes are, in fact, something far stranger. Maybe they conceal a wormhole core. To give a sense of the mind-bending possibilities, a wormhole inside a star could mean that what we see as a bright point in the night sky is not just nuclear fusion lighting up gas, but the entrance to a tunnel through reality. Its gravitational pull, its radiation, its flickers of energy could all be signs of that hidden passage. If true, then every time we gaze at such a star, we might be staring at the very edge of our universe, with the other side leading somewhere entirely new. This is why wormholes matter to our discussion. Without them, the idea of stars as portals collapses. With them, even if only theoretically, the door opens wide to some of the most astonishing possibilities ever proposed in science. Wormholes give us the vocabulary to imagine how a star could function not just as a beacon of light, but as a bridge across time, space, and reality itself. Now that we've explored what a wormhole is, the natural next question arises. Where might such things exist in the real universe? And here, the idea becomes both thrilling and unnerving, because some scientists suggest that stars themselves, or at least certain kinds of stars, could serve as the entrances to wormholes. On the surface, stars appear to be the most ordinary objects in the night sky. They are the building blocks of galaxies, the engines of cosmic chemistry, the light sources that make life possible. But deep inside some of these stars, or in the remnants they leave behind, conditions could be so extreme that space-time itself is reshaped into something far stranger than we can presently confirm. Let's start with the simple reasoning. Stars are massive concentrations of matter, and gravity is what shapes their lives. The more massive a star, the more its gravity bends the space-time around it. At the lower end, this creates a stable star like our Sun. At the extreme end, the collapse of a star can form a black hole, a region of such intense curvature that nothing, not even light, can escape. If wormholes are possible, then these gravitational extremes are precisely where they might form. That is why stars, or the objects they evolve into, become the prime candidates for natural wormhole entrances. Now, why would scientists suspect such a thing? The answer lies in how similar black holes and wormholes look mathematically. In Einstein's equations, the solutions that describe black holes can also be tweaked to describe wormholes. In fact, the earliest Einstein-Rosen bridge was originally proposed as a model for what the inside of a black hole might look like. The challenge, however, is that black holes lead to singularities, points of infinite density where physics as we know it breaks down, while wormholes offer a potential bypass of those singularities. If, instead of collapsing into a singularity, a star's core could stabilize into a wormhole throat, then the object would still look very much like a black hole from the outside but would hide a very different interior. This gives rise to the provocative idea of exotic stars. These are not ordinary stars like the Sun or red giants, but rather hypothetical stellar objects that might form under conditions not yet observed, or that might be masquerading in plain sight as things we already know, such as neutron stars or black holes. If some of these exotic stars conceal wormhole entrances, then the universe might be filled with natural gateways that we simply haven't recognized for what they are. Think about the implications. Astronomers have catalogued billions of stars across the cosmos. We know many of them by type, by size, by spectral signature. Yet among them, it's possible that a handful are not what they seem. Some might be acting as natural bridges, their immense gravity holding open a tunnel that leads far away, or perhaps to someplace wholly outside our universe. From Earth, they may look like nothing more than faint points of light or regions of darkness where stars should be. But if we could somehow approach one closely, its true nature might reveal itself. Of course, no telescope today can peer inside the core of a distant star to confirm such a wild idea. Instead, physicists rely on indirect reasoning. They study the equations of general relativity, the physics of collapse, and the exotic conditions inside dense objects to ask, could this environment support a wormhole instead of a singularity? The answer, at least theoretically, is yes. If certain energy conditions are met, and if exotic matter could exist to stabilize the tunnel, then a star might indeed serve as a wormhole entrance. There's also the tantalizing possibility that we may have already mistaken such objects for something else. For instance, what if some of the black holes we've detected through their gravitational influence or their X-ray emissions are not true black holes, but wormhole stars in disguise? What if the anomalies we occasionally see, bursts of unexplained radiation, gravitational lensing that doesn't quite match predictions, are hints of wormhole activity rather than random cosmic noise? These are open questions, and while mainstream astronomy remains cautious, the door isn't shut. This is why stars make such compelling candidates in the wormhole discussion. They are natural cosmic laboratories, places where gravity is pushed to its limits. They are abundant, scattered across every corner of the cosmos. And they already hide mysteries we don't fully understand. If wormholes exist anywhere, then stars, or the exotic remnants of stars, are among the most logical places to look. What makes some stars or compact cosmic objects special enough to be suspected of hiding wormhole-like properties? To answer this, we have to take a closer look at the extreme physics that occurs in these objects and why they capture the attention of scientists who dare to stretch Einstein's equations to their limits. The first thing that makes them stand out is gravity itself. Normal stars, like our Sun, balance two opposing forces: the inward pull of gravity trying to collapse the star and the outward push of pressure from nuclear fusion in the core. That equilibrium creates stability and allows the star to shine for billions of years. But when stars exhaust their nuclear fuel, gravity often wins. If the collapsing star is massive enough, no known force can stop the implosion, and spacetime itself caves in. This collapse is where the doorway to the truly exotic opens. In ordinary astrophysics, the end product is a black hole. But in theoretical physics, it could also mean the birth of a wormhole. The reason is surprisingly simple. The math describing black holes and wormholes looks eerily similar. Both involve regions where spacetime is curved to an extreme degree. Both involve horizons beyond which information behaves in strange ways. But in wormhole models, instead of collapsing into a singularity, spacetime bends into a bridge that could connect to another region. The difference is subtle but profound. Where one path leads to infinite density and an inescapable end, the other potentially leads to a passageway, something like a tunnel carved through the fabric of existence itself. Another reason some objects are suspected of having wormhole-like properties is their apparent ability to defy expectations. Astronomers have observed certain stars and compact objects behaving oddly. Unusual bursts of energy, radiation spectra that don't quite match black hole models, and gravitational lensing effects that hint at something more complex than a simple point of collapse. While none of these observations provide proof, they fuel speculation that at least some of these anomalies could be explained if the objects were wormholes, or contained wormhole-like structures at their cores. There's also the concept of symmetry that intrigues physicists. A black hole represents an ultimate in, a place where matter falls, but never emerges. For the equations of general relativity to be fully balanced, some theorists argue there should also exist an ultimate out, a counterpart object where matter emerges, perhaps from another part of the universe. This idea gave rise to the concept of white holes, which we'll explore in more detail later. The intriguing part is that wormholes naturally connect the two ideas. One end functions like a black hole entrance, the other like a white hole exit. Certain exotic stars could therefore be suspected of harboring this symmetry inside their cores. What also makes these objects special is their role as natural laboratories of exotic matter and energy. Inside the most extreme stars, pressures and densities are so far beyond what we can replicate on Earth that new forms of matter might exist. Theoretical constructs like quark matter, bosonic condensates, or even entirely unknown states of matter could be present. And it's precisely these unusual conditions that might allow wormholes to form or stabilize. To scientists, stars provide the only real chance to test such possibilities, even indirectly, because no experiment on Earth could ever reproduce the same extremes. Furthermore, stars that could harbor wormholes would not be just unusual, they'd be revolutionary. They would be different from anything else we've encountered, not simply because they bend light or pull at nearby objects with great force, but because they might act as bridges across reality. That potential is what makes them so fascinating. Even if the chance is slim, the mere possibility compels scientists to study them, to keep refining our observational tools, and to recheck the assumptions we've made about what stars and compact objects truly are. In short, what makes some stars special enough to be suspected of wormhole-like properties is their extremity, their strangeness, and the ways in which they push physics beyond familiar ground. They are cosmic enigmas that sit at the edge of what we can explain, behaving in ways that might reveal deeper truths about space-time itself. And if those truths turn out to involve wormholes, then these stars are not merely special, they are extraordinary, the keys to unlocking a universe far larger and stranger than we've dared to believe. When the subject of wormholes comes up, it's almost impossible not to immediately think of black holes. The two concepts are intertwined in both physics and popular imagination, and for good reason. They both emerge from Einstein's equations of general relativity, and they both represent spacetime pushed to its absolute extremes. Yet the differences between them are just as striking as the similarities. And understanding those differences is essential if we want to explore the possibility that some stars might conceal wormhole cores instead of singularities. A black hole is often described as a one-way door. It forms when a massive star collapses under its own gravity, compressing its mass into such a small region that not even light can escape its pull. The boundary that marks this point of no return is called the event horizon. Once something crosses the horizon, whether it's a photon of light, a particle of matter, or even a planet, it is trapped forever. At the very center lies what current physics calls a singularity, a point of infinite density where the laws of physics as we know them break down. In practice, a black hole is a cosmic trap. Matter goes in, but nothing comes out. Now compare this to a wormhole. On the surface, it can look very much like a black hole. From a distance, a wormhole's mouth could exert a similar gravitational pull, warping light and space in the same way a black hole does. But the crucial difference lies inside. Instead of a singularity at the core, a wormhole contains a tunnel, a throat, that connects two different regions of spacetime. That second region could be elsewhere in our universe, or it could lead to an entirely different universe altogether. If a wormhole is stable, matter that falls in one side could, in principle, pass through and exit from the other side. In other words, where a black hole is an end, a wormhole could be a passage. This distinction has profound implications. Imagine two stars, one collapsing into a traditional black hole, and another collapsing into a wormhole entrance. To an outside observer, they might look nearly identical, both dark, both pulling strongly on nearby objects, both distorting the space around them. But their fates are completely different. The black hole becomes a prison, hoarding matter and information in a way that leads to deep puzzles like the information paradox. The wormhole, by contrast, becomes a bridge, a gateway that not only swallows matter but also releases it elsewhere. One object represents a cosmic cul-de-sac, the other a cosmic highway. There's another subtle but important difference: time. In a black hole, as you approach the event horizon, time itself slows relative to an outside observer, and inside the horizon, all paths lead toward the singularity. In a wormhole, however, the geometry can allow for paths that don't end in destruction. Depending on how the wormhole is configured, it could even permit time travel, though such scenarios often lead to paradoxes that physicists struggle to reconcile. Still, the mere possibility makes wormholes uniquely fascinating, while black holes remain forbidding and final. Scientists often describe black holes as solutions to Einstein's equations that are known to exist, while wormholes are solutions that might exist under very special circumstances. Both emerge naturally from the mathematics of space-time curvature, but black holes require no exotic conditions, just enough mass collapsing under gravity. Wormholes, on the other hand, require stabilization through exotic matter or negative energy, which has never been observed in quantities large enough to sustain a cosmic tunnel. That's why black holes are accepted as real, while wormholes remain speculative. Yet, it's exactly this similarity that keeps scientists interested. If wormholes are mathematically so close to black holes, and if they could masquerade as one, then maybe some of the black holes we've already catalogued are not what they appear to be. Perhaps hidden among them are wormhole stars, objects that look like traps but are actually doorways. Distinguishing between the two is one of the grand challenges of modern astrophysics. In the end, the key difference can be summed up in one idea. Black holes are cosmic endpoints, while wormholes, if they exist and are stable, are cosmic shortcuts. One locks matter away forever. The other potentially unlocks entire new realms of existence. And that is why the question of whether some stars might hide wormhole cores is so compelling. Because the difference between black holes and wormholes is the difference between finality and possibility. The concept of the core hypothesis pushes the boundaries of astrophysics and imagination alike. Traditionally, when we think about the life cycle of massive stars, the narrative is clear. Once their nuclear fuel is exhausted, gravity takes over. For medium-mass stars, this collapse leads to neutron stars, dense, city-sized remnants. For truly massive stars, the collapse continues unchecked, producing black holes with singularities at their cores. But what if that final step is not the only option? What if, instead of collapsing into an infinitely dense singularity, the core of some stars evolves into something different? A wormhole throat, a gateway rather than a dead end. This is the heart of the wormhole core hypothesis. To grasp why this idea is so powerful, we need to revisit what makes a singularity such a troubling concept. A singularity is essentially a point where space-time curvature becomes infinite and the known laws of physics cease to function. Mathematically, black hole solutions predict singularities, but physically, many scientists find them unsatisfying. Nature, they argue, tends to avoid infinities. If singularities are signs of our incomplete understanding, then perhaps what lies inside a black hole, or inside certain collapsed stars, isn't infinite density, but a new kind of structure that our current theories only partially describe. One candidate for such a structure is a wormhole core. Imagine the collapse of a massive star. Instead of space-time pinching off into a singularity, the core stabilizes into a tunnel-like geometry. This geometry, known in theoretical physics as a wormhole throat, acts as a passageway rather than a termination point. To an external observer, the star might still resemble a black hole. It could have an event horizon, extreme gravity, and a dark exterior. But its interior would tell a completely different story. Rather than crushing matter into oblivion, it would funnel matter and possibly information into another region of space-time. The plausibility of this idea stems from the fact that general relativity allows wormhole solutions under certain conditions. The mathematics doesn't forbid a wormhole replacing a singularity. It merely requires the right balance of energy conditions. In this sense, the wormhole core hypothesis is not science fiction. It's a serious, if speculative, extension of established physics. The key challenge is stability. Without exotic matter or negative energy, most wormholes collapse instantly. Yet if nature has a way to generate the required conditions inside stellar cores, then wormhole stars could exist. One fascinating implication of this hypothesis is that some of the compact objects we call black holes may not be black holes at all. Their gravitational pull, radiation signatures, and influence on nearby stars might look nearly identical to what we expect from black holes. But deep inside, instead of a singularity, there could be a wormhole throat, a cosmic bridge masquerading as a dead-end collapse. To astronomers observing from Earth, the distinction would be subtle, perhaps only detectable through anomalies such as unexpected bursts of radiation, gravitational waves with unusual patterns, or deviations in how matter accretes around the object. This idea also provides an elegant way to address the black hole information paradox, one of the thorniest puzzles in modern physics. If information entering a black hole is not lost to a singularity but instead passes through a wormhole core to another region of spacetime, then the paradox dissolves. Information is preserved, just hidden in a realm beyond our detection. That would mean wormhole cores are not just exotic curiosities but potential keys to resolving some of the deepest mysteries in theoretical physics. Of course, skeptics rightly point out that we have no direct evidence for wormhole cores. They remain speculative until proven otherwise. But history reminds us that speculation often precedes discovery. Black holes themselves were once dismissed as mathematical oddities, too strange to be real. Today, we photograph their shadows. It's not unreasonable to imagine that wormhole cores, too, may transition from speculation to observation in the future, especially as telescopes grow more powerful and as our theoretical models sharpen. In summary, the core hypothesis suggests that inside certain stars, particularly those undergoing extreme gravitational collapse, the end result might not be a singularity but a wormhole throat. This would transform such stars into cosmic gateways, objects that only appear to be endpoints but are, in fact, bridges. If true, then some of the darkest objects in the universe are not tombs of matter and light but doors waiting to be unlocked. The energy conditions problem lies at the very heart of the wormhole debate. While wormholes are mathematically allowed in Einstein's theory of general relativity, their survival requires something that doesn't exist in ordinary astrophysics: exotic matter or negative energy. Without it, the geometry of a wormhole would collapse instantly, snapping shut like a rubber band pulled too tight. To understand why, we need to look closely at how energy and spacetime interact. In general relativity, matter and energy tell spacetime how to curve, and spacetime curvature tells matter how to move. This intimate relationship is described by Einstein's field equations, which balance the geometry of spacetime against the stress-energy tensor, essentially a ledger of all the mass, momentum, pressure, and energy in a region. For ordinary matter, stars, planets, people, the energy is always positive. This positivity is what makes gravity universally attractive. It's why planets orbit stars, why galaxies cluster, and why collapsing stars form black holes. Positive energy density bends space-time inward. But wormholes, by their very design, require the opposite. To hold open the throat of a wormhole and prevent it from collapsing, space-time must curve in a way that defies the usual rules. That means you need regions where energy density is effectively negative. Negative energy creates repulsion instead of attraction. It pushes space-time outward, counteracting the natural tendency of gravity to close the tunnel. Without this repulsive component, a wormhole throat would collapse faster than anything could pass through it. The concept of negative energy may sound like science fiction, but physics does provide examples. The Casimir effect, for instance, demonstrates that quantum fluctuations in empty space can create regions of negative energy between two closely spaced plates. In laboratories, this effect has been measured, tiny, but real. The catch is scale. The amount of negative energy required to stabilize even a small wormhole is astronomically larger than anything we can currently generate or manipulate. Still, its existence in principle keeps the door open. Exotic matter is another way of describing what's needed. Unlike ordinary matter, which obeys the so-called energy conditions of relativity, such as always having positive energy density, exotic matter would violate them. It might have unusual properties, such as negative mass, repulsive gravity, or pressure so strange that it defies classical intuition. While no one has ever detected exotic matter, it's a theoretical placeholder for the kind of substance that could keep wormholes open. In essence, it's the scaffolding that would hold the throat from collapsing under the crushing weight of normal spacetime curvature. Some physicists speculate that inside the densest regions of the cosmos, inside collapsing stars, at the edges of black holes, or near the Big Bang, conditions might briefly give rise to exotic matter. If that's true, then nature itself could produce the ingredients necessary for wormhole stability. Stars, especially those collapsing under immense gravitational pressures, become natural candidates because they already approach the limits of what matter and energy can endure. The idea of wormhole cores inside such stars hinges on the possibility that exotic physics activates under these conditions. Quantum theory also hints at possible loopholes. Quantum fields are never truly empty, and their fluctuations might allow for temporary violations of the energy conditions required to stabilize wormholes. Theoretical frameworks such as semi-classical gravity explore whether quantum effects on spacetime could keep a wormhole open long enough for information, or even matter, to pass through. While we're far from knowing for sure, the interplay between quantum physics and gravity remains one of the most promising avenues to test whether exotic matter or negative energy could exist on astrophysical scales. The implications of this are enormous. If negative energy and exotic matter are more than theoretical curiosities, they could do more than stabilize wormholes. They might revolutionize propulsion, shielding, even our understanding of cosmology itself. But if they do not exist in nature, or if they exist but cannot be harnessed, then wormholes remain nothing more than unstable curiosities, collapsing the moment they form. In short, the energy conditions represent both the greatest obstacle and the greatest hope in the search for wormhole stars. They are the reason wormholes are still in the realm of speculation, but they are also the reason scientists cannot completely dismiss them. The possibility that exotic physics could keep a wormhole core alive inside a star is tantalizing because it would mean that the universe is capable of engineering structures far stranger than anything we've imagined, and that the stars we see could, quite literally, be gateways made stable by physics we don't yet fully understand. If black holes are the ultimate indoors of the universe, then white holes are their theoretical outdoors. The concept of white holes emerges naturally from the mathematics of general relativity, and it's closely tied to the wormhole discussion. Where a black hole traps everything, matter, light, information, behind its event horizon, a white hole would do the exact opposite. Nothing could enter it, but matter and radiation could pour outward. In this sense, a white hole is a time-reversed black hole. One consumes, the other expels. At first, the idea of white holes seems absurd. How can there be an object that endlessly emits energy and particles without ever taking anything in? Yet when Einstein and Rosen proposed their famous bridge in 1935, the Einstein-Rosen bridge, they discovered that the equations describing black holes also admitted another solution, one that looked like the mirror image of a black hole. This mirror solution was the white hole. At the mathematical level, a black hole and a white hole are two ends of the same structure, linked by a tunnel, a wormhole. This connection is fascinating because it provides a natural way to visualize what a wormhole would look like in action. Imagine a massive star collapsing into what we perceive as a black hole. Its event horizon forms, and matter falls inward, disappearing from view. But on the other side of the wormhole throat, instead of a singularity, there could be a white hole. To observers in that other region of spacetime, the white hole would appear as a brilliant, mysterious source, spewing out matter and radiation that seem to come from nowhere. In essence, the black hole swallows, and the white hole regurgitates. This duality adds an elegant symmetry to the universe. It balances the idea of information and matter being lost in black holes by suggesting they might simply be transported elsewhere and expelled through white holes. For some theorists, this connection even provides a possible solution to the information paradox. What falls into a black hole may not be destroyed but may instead reappear, carried through a wormhole and emitted by a white hole. From our perspective, it looks like annihilation. From the universe's perspective, it's just a transfer. Now, have we ever observed a white hole? Not directly. In fact, no evidence currently exists that they are real physical objects. Most physicists consider them purely theoretical, and many argue that they are inherently unstable. If a white hole existed, it would likely collapse or transform almost instantly upon contact with surrounding matter. However, the idea continues to attract attention because it fits so neatly into the wormhole framework. A traversable wormhole, in its simplest depiction, would be a tunnel with a black hole entrance on one side and a white hole exit on the other. Some researchers have even speculated that unusual astrophysical phenomena might be white hole candidates. For example, certain unexplained bursts of gamma rays or cosmic rays, sudden emissions of high-energy particles that don't match conventional models, could, in principle, be linked to white hole-like behavior. These suggestions remain speculative, but they highlight the fact that we still don't fully understand all the energy sources in the cosmos. What we label as mystery bursts today could one day be reinterpreted as windows into wormhole activity. The white hole connection also stimulates philosophical wonder. If a wormhole star exists, then on the far side of its core there may be a region where matter is not being consumed but expelled. That could mean that some of the strange, unexplained stars or energy sources we see in deep space might actually be wormhole exits, objects that are not self-powered but are instead fed by the collapse of stars elsewhere in the universe. In this way, Black holes and white holes would not be isolated phenomena but complementary parts of a larger cosmic cycle. Even though mainstream science remains skeptical, the white hole connection is one of the most beautiful features of wormhole theory. It doesn't just add symmetry, it provides a framework for imagining wormholes as more than abstract geometry. If black holes are mouths that endlessly consume, then white holes are the mouths that endlessly speak, and together they complete the bridge. For stars suspected of hiding wormhole cores, this means they might not just lead to another region of space, they might ultimately lead to another star-like object radiating the universe's hidden traffic back into existence. If some stars or compact objects really do conceal wormhole cores, the question then becomes, how would we know? Astronomers cannot fly up to a black hole candidate, dive inside, and check whether it leads somewhere else. The distances are too vast, and the environments around these objects are too extreme. Instead, scientists must rely on indirect evidence. Tiny deviations from what is expected, strange signatures that don't quite align with our models of black holes, neutron stars, or other familiar objects. These possible signs are what we might call observational clues, and they are the only path forward in testing whether wormhole stars could actually exist. One of the first things astronomers would look for is unusual radiation. Black holes, by their nature, should not emit light directly, since nothing escapes from inside the event horizon. The radiation we do see from black holes typically comes from their surroundings, as gas and dust spiral inward, heating up in an accretion disk before crossing the horizon. If an object suspected of being a black hole were to emit bursts of light or energy from within the event horizon itself, that would be a major anomaly, something not easily explained. Some theorists suggest that if a black hole candidate is actually a wormhole, occasional leaks of radiation or jets of energy could escape from the throat, betraying its true identity. Another potential clue lies in gravitational lensing, the way massive objects bend light from stars or galaxies behind them. Black holes are expected to create precise patterns of lensing, distorting the background light in predictable ways. But a wormhole, with its tunnel-like geometry, might bend light differently. Depending on how the wormhole connects two regions of space, it could produce unusual distortions, rings of light that don't match black hole models, or flickering effects that suggest light is passing through a hidden tunnel. Detecting such anomalies would require incredibly precise instruments, but as telescopes improve, especially with the rise of space-based observatories, the possibility becomes less remote. Gravitational waves provide another avenue of exploration. When two black holes collide, they send ripples through space-time that we can now detect thanks to instruments like LIGO and Virgo. These signals have a very specific profile, a rise in frequency and amplitude as the objects spiral together, followed by a dramatic peak and then a fading ring-down. If wormhole stars exist, their collisions might produce gravitational waves that deviate subtly from this expected pattern. For instance, echoes, faint, delayed signals following the main event, could indicate that the objects were not true black holes but had internal structures, possibly wormhole throats. Some tentative hints of such echoes have already been discussed in the scientific community, though none are yet confirmed. Unusual motion of nearby stars can also provide indirect evidence. Around the black hole at the center of our galaxy, Sagittarius A, astronomers track stars that orbit in tight, fast ellipses. The orbits match black hole predictions very well, but if a wormhole star were present, its gravitational influence might differ in subtle ways. For example, stars might shift slightly off their expected paths, or their velocities might change unexpectedly. Such deviations could be fingerprints of a hidden wormhole geometry, though separating them from other astrophysical noise is a monumental challenge. There are also speculative ideas that wormhole stars could produce sudden, unexplained bursts of energy, perhaps resembling fast radio bursts, FRBs, the mysterious, millisecond-long signals detected from distant galaxies. While mainstream explanations for FRBs focus on neutron stars or magnetars, the possibility remains that some could be tied to wormhole activity. Matter passing through, interacting with the wormhole throat, and releasing energy in ways we don't yet understand. Even Hawking radiation, the faint glow predicted to seep from black holes due to quantum effects, could play a role. If astronomers detected radiation that didn't quite fit the expected Hawking profile, radiation too strong, too irregular, or emerging from objects that shouldn't have it, that might suggest an alternative explanation. A wormhole leaking energy would be one possibility. In practice, None of these clues on their own would be definitive. The cosmos is messy, and there are often multiple explanations for strange observations. But by piecing together radiation patterns, gravitational lensing effects, wave signals, and energy bursts, astronomers hope to build a case. If several anomalies consistently point away from black hole behavior and towards something more exotic, then the wormhole hypothesis would gain traction. For now, the evidence is tantalizing but inconclusive, leaving open the possibility that some of the stars we see, or some of the black hole candidates we've catalogued, are not what they seem, but are instead cosmic gateways whose true nature is waiting to be revealed. The greatest obstacle to wormholes being real, functioning gateways rather than mathematical curiosities is their stability problem. Even though general relativity allows wormhole solutions, the brutal truth is that most wormholes, if they could form naturally, would collapse almost instantly, sealing shut before anything, even a single photon, could make it through. Understanding why brings us to the harsh interplay between geometry, gravity, and the need for exotic matter. At the core of the problem lies gravity itself. In Einstein's framework, mass and energy warp space-time, and the more mass you concentrate in a region, the stronger the inward pull becomes. A wormhole throat is, by design, a region where space-time bends back on itself, creating a tunnel-like structure. The walls of this tunnel want to collapse under gravity's relentless attraction. Without something to hold them apart, the wormhole closes the moment it's created. Imagine trying to hold open the neck of a balloon while the air rushes out. The natural forces are all pushing toward collapse, and you need something unnatural to keep it open. This something unnatural is exotic matter or negative energy. Ordinary matter, stars, planets, dust, even the gas fueling fusion, always has positive energy density, and positive energy only strengthens the collapse. To counteract that, wormholes require matter with negative energy density, a form of material that would create repulsive gravitational effects. In theory, this could balance the inward pull of gravity and keep the throat open long enough for matter, or even entire spacecraft, to pass through. Without exotic matter, though, wormholes die the moment they are born. The instability is not just a matter of collapse, but also of violent feedback. If even a trickle of radiation or matter tries to pass through a natural, unstabilized wormhole, its energy adds to the stress on space-time. That stress amplifies the collapse, snapping the throat shut more quickly. In other words, the very act of using a wormhole destroys it, unless some stabilizing mechanism is in place. This is why physicists argue that traversable wormholes, the kind popularized in science fiction, cannot exist without exotic matter. Even in the vacuum of space, wormholes face another enemy: quantum fluctuations. At the smallest scales, the universe is never still. Energy jitters in and out of existence in what's known as the quantum foam. These fluctuations can disrupt the delicate balance required to keep a wormhole open. Some models show that unless negative energy actively stabilizes the wormhole, quantum effects alone would make it collapse instantly. It's a reminder that the universe is not forgiving when it comes to maintaining such fragile geometries. There are thought experiments that drive this instability home. Suppose a wormhole throat did exist, held open just barely by the geometry of space-time. As soon as one particle of light enters, its energy increases the curvature, which narrows the throat. That narrowing intensifies the gravity, which accelerates the collapse, until the passage closes entirely. The process is so fast it makes wormholes effectively unusable unless exotic physics intervenes. From the outside, such a wormhole might resemble a black hole, dark, gravitationally powerful, and seemingly permanent. But internally, it would not function as a bridge. This instability is why wormholes remain speculative. Black holes, by contrast, don't require anything exotic to exist. All they need is enough mass collapsing under gravity, and nature produces them regularly. Wormholes, on the other hand, demand both extreme conditions and new physics. Without that exotic matter, they collapse faster than the blink of an eye. This is also why many physicists view wormholes more as tools for exploring the limits of relativity than as physical objects likely to be found in the cosmos. And yet, the stability problem doesn't kill the dream, it just makes it more intriguing. It forces us to ask, could exotic matter exist naturally inside stars, perhaps created under the unimaginable densities of a collapsing core? Could quantum effects, under the right circumstances, provide the repulsive push needed to hold a wormhole throat open for longer than a fleeting instant? If so, then the stability problem, while immense, might not be insurmountable. Wormhole stars could be rare, fragile, and fleeting, but not impossible. In the end, the stability problem is both the wormhole's greatest weakness and its greatest challenge. It draws a sharp line between what is mathematically possible and what might be physically real. And until we find evidence of exotic matter or a natural process that stabilizes wormholes, the dream of stars as cosmic gateways will remain perched delicately on the edge between speculation and reality. When we talk about the possibility of wormhole cores inside stars, it's important to acknowledge that physics doesn't stop at the familiar. Beyond neutron stars, white dwarfs, and black holes lies a whole catalogue of exotic star models. Theoretical constructs that might exist under conditions so extreme that ordinary matter transforms into entirely new states. These exotic stars are not proven to exist, but they arise naturally from equations that extend or modify our understanding of gravity and quantum fields. What makes them particularly interesting for our discussion is that several of these exotic models could mimic wormhole-like behavior, acting in ways that blur the line between collapsed stars and hidden cosmic gateways. One of the most intriguing candidates is the boson star. Unlike ordinary stars, which are composed of fermions, particles like protons, neutrons, and electrons, boson stars are theorized to form from bosons, particles that obey very different quantum rules. While fermions resist being packed too tightly due to the Pauli exclusion principle, bosons can occupy the same quantum state, piling together without that resistance. If enough bosons clump under gravity, the result could be a stable star-like object held together not by nuclear fusion, but by the collective quantum state of its particles. What's fascinating is that boson stars could be transparent, nearly invisible, and might imitate the gravitational pull of black holes without possessing a singularity. In some models, boson stars can even form stable structures that resemble wormhole throats, their unusual matter acting as the exotic scaffolding needed to keep a tunnel open. Another proposal is the gravastar, short for gravitational vacuum star. This model suggests that when a massive star collapses, instead of forming a singularity, the core transitions into a bubble of exotic vacuum energy. Around this bubble forms a thin shell of ultradense matter, balancing the pressure inward and outward. From afar, a gravastar would look almost identical to a black hole, dark, compact, and gravitationally intense. But inside, there would be no singularity, no event horizon, only a strange interior structure supported by vacuum energy. Some physicists have argued that gravastars could serve as natural wormhole mimics, since their exotic interiors might allow for tunnel-like geometries without collapsing. There are also models like quark stars and preon stars, which extend the idea of neutron stars into deeper realms of matter. In a neutron star, neutrons are crushed into a dense, city-sized ball. But at even higher pressures, those neutrons might dissolve into their constituent quarks, forming a quark star. Push the collapse further, and you might reach hypothetical preons, particles even smaller than quarks. These stars, though still speculative, represent stages of matter that edge toward the exotic. While not wormholes themselves, their strange internal pressures and densities could hint at pathways toward conditions favorable for wormhole stabilization. There's also speculation about dark matter stars, objects composed primarily of the mysterious dark matter that makes up most of the universe's mass. Since dark matter interacts weakly with normal matter, such stars could be nearly invisible, detected only through their gravity. Some theories suggest that if dark matter includes exotic particles, their collective behavior could create stable, star-like objects that blur the line between ordinary astrophysics and the kind of exotic conditions wormholes would require. What unites all these exotic star models is that they challenge the assumption that gravitational collapse must always lead to singularities. Instead, they propose alternative structures, bosonic condensates, vacuum shells, quark matter, or dark matter, that resist collapse in ways unfamiliar to us. These structures, in turn, provide natural laboratories for wormhole-like geometries. For instance, a boson star with sufficient negative pressure could mimic the exotic matter needed to keep a wormhole throat open. A gravastar's vacuum bubble might serve as the repulsive engine preventing collapse. The fascinating part is that to an astronomer observing from a distance, many of these exotic stars would look almost indistinguishable from black holes. Their gravitational pull, their influence on nearby stars, even their accretion disks might all appear nearly identical. But inside, the story would be very different. Where a black hole hides a singularity, these exotic stars hide new physics, and possibly the conditions necessary for wormhole cores. If such exotic stars exist, then some of the black hole candidates we've catalogued may not be black holes at all. They could be boson stars, gravastars, or something even stranger. And if even a fraction of those exotic stars can support wormhole-like structures, then the universe may already be sprinkled with natural gateways, hidden in plain sight, masquerading as ordinary dark objects. If computer simulations have taught us anything about modern physics, it's that equations on a page often hide wild, non-intuitive behavior that only reveals itself when you actually let the dynamics run forward in time. The same is true for the wormhole core hypothesis. While analytic solutions to Einstein's equations point to the mathematical possibility of tunnels through spacetime, it is numerical experiments, large-scale simulations using the full machinery of numerical relativity and field theory, that let researchers test whether such structures could form, persist, or leave observable fingerprints. Over the last few decades, an increasingly sophisticated suite of computer models has sketched plausible scenarios in which stellar collapse, exotic fields, or engineered matter distributions produce throat-like geometries. Those models don't prove wormhole stars exist, but they do show the concept is not purely symbolic. Under certain conditions, simulated spacetimes can and do behave like tunnels. At the heart of these simulations are the Einstein field equations coupled to matter models, fluid dynamics for ordinary stellar gas, scalar or vector fields to model hypothetical exotic components, and sometimes semi-classical corrections to approximate quantum effects. Early numerical work used simplified, spherically symmetric setups because those require much less computational power. They allowed researchers to probe core questions like whether a collapse can avoid singularity formation or whether a throat can be momentarily supported. More modern work abandons symmetry assumptions and runs fully three-dimensional simulations using parallel supercomputers, evolving spacetime and matter self-consistently. Code such as the Einstein toolkit and others built on adaptive mesh refinement let teams follow nonlinear dynamics from initial data all the way through violent collapse, bounce, and post-collapse relaxation. One class of simulation replaces the usual matter of a collapsing star with a phantom scalar field, a field with a reverse sign kinetic term that effectively provides negative energy density. When evolved, these models demonstrate that a collapsing configuration can, under tuned conditions, transition to a geometry with a minimal area surface, a throat, connecting two asymptotic regions. The throat's radius depends sensitively on the field parameters. Make the negative energy component too small and the throat pinches off rapidly, too large and the configuration either disperses or evolves into a horizon-forming collapse. These numerical experiments are instructive because they explicitly show the dynamical competition between collapse and the repulsive effect of negative energy fields. They also illustrate the time scales involved. Many simulated wormhole throats exist only transiently, opening and closing on timescales comparable to the dynamical time of the collapsing object, fractions of a second for stellar mass systems, reinforcing the need for robust stabilization mechanisms if natural, traversable wormholes are to persist. Other simulations focus on more physically motivated exotic matter candidates. For example, boson star models, self-gravitating condensates of scalar or complex fields, have been studied extensively with numerical relativity. When two boson stars collide or when a boson star accretes matter, the non-Linz evolution can produce compact, horizonless objects whose effective spacetime geometry resembles that of a wormhole throat under certain conditions. These results are tantalizing because boson stars are arguably less exotic than phantom fields. They can arise from scalar particles that obey ordinary quantum mechanics. Nonetheless, the simulations indicate that achieving a long-lived throat still typically requires fine-tuning of parameters, mass, self-interaction strength, field phase, and that the resulting objects are delicate, sensitive to perturbations and prone to collapse into black holes or to disperse. A closely related line of computational work examines gravastar-like transitions. In these models, collapse triggers a phase transition of the vacuum in the core region, numerically modeled by matching an interior region with negative pressure, a de Sitter-like vacuum, to an exterior Schwarzschild geometry across a thin shell of matter. Time-dependent simulations that incorporate shell dynamics show that, under the right tension and surface energy conditions, the shell can settle into a quasi-stable configuration, avoiding horizon formation. The interior vacuum region can mimic the repulsive effects required to hold open a throat-like structure, and when perturbed, The shell responds by oscillating rather than catastrophically collapsing. These computations are important because they show a plausible mechanism in which known-seeming physics, vacuum energy, phase transitions, could produce wormhole-mimicking, horizonless remnants. Beyond constructing candidate throats, simulations have been crucial in predicting observational signatures that could, in principle, distinguish wormhole-like objects from black holes. Ray tracing codes that propagate light through numerically generated spacetimes reveal distinct imaging features, shadows with different brightness distributions, lensing rings that are displaced or duplicated due to light passing through the throat and emerging in another region, and time-dependent echoes in photon arrival times as light circumnavigates exotic interior structures. When these ray tracing routines are combined with models of accretion flows, magneto-hydrodynamic simulations of plasma swirling in strong gravity, the synthetic images start to look like what telescopes such as the Event Horizon Telescope, EHT, might see. Several groups have produced simulated shadow images for traversable wormhole metrics and found measurable differences in the detailed intensity distribution, which encourages using high-resolution imaging as a discriminant. Gravitational wave simulations are another fertile ground. Numerical relativity teams have run mergers involving horizonless compact objects like boson stars or exotic star analogues and computed the gravitational waveforms. These waveforms can deviate noticeably from standard black hole merger signatures. One especially interesting prediction that keeps recurring is the possibility of post-merger echoes, reverberations that occur when gravitational radiation reflects off an inner structure, such as a throat or a dense shell, and leaks back out over time. Several tentative claims of echoes in LIGO or Virgo data have been debated fiercely in the literature. Simulations are indispensable for quantifying what echoes would look like for different throat geometries and matter models, and for estimating their amplitude and time delay relative to the main merger signal. Simulations have also explored formation channels that don't rely on pre-existing exotic fields. Bubble nucleation during cosmological phase transitions, collisions of topological defects like cosmic strings, or quantum tunneling events in the early universe have all been modeled to assess whether they could seed a macroscopic throat that later becomes embedded in a star. These scenarios are computationally challenging because they mix cosmological scales, field theory microphysics, and general relativity. But progress has been made using lattice simulations coupled to evolving metrics. Some results suggest that under very particular circumstances, a topology change can produce a localized region with wormhole-like connectivity, which later accretes normal matter and might masquerade as a compact star. The caveat, again, is that these events are rare and the resulting structures are often unstable without further exotic stabilization. Despite the imaginative successes, simulations also make the skepticism explicit. When researchers include more realistic physics, full three-dimensional perturbations, magnetic fields, radiation transport, finite temperature equations of state, the fragile throats almost always succumb to instabilities unless the exotic component is unrealistically large or finely tuned. Back reaction effects, where the quantum fields meant to stabilize the throat feed back on the geometry, frequently drive the system towards collapse. Moreover, semi-classical approximations used to model quantum effects are themselves of limited reliability in regions of extreme curvature. A true quantum gravity treatment is beyond current computational capability. Thus, simulated wormholes often serve as proofs of principle rather than robust astrophysical predictions. Simulations also illuminate the parameter regimes where wormhole-like behavior might be observationally relevant. For stellar mass scales, throat lifetimes in most models are short, suggesting that if wormhole cores exist in stars, they may be transient or only intermittently traversable. For supermassive scales, the dynamical times are longer, and numerical work hints that longer-lived exotic configurations could be possible, as the larger spatial scales reduce quantum back reaction severity per unit volume. This scale dependence has motivated targeted searches in observational datasets. If wormhole stars exist, they may preferentially appear as anomalies in the population of supermassive compact objects, or as rare transient events in time domain surveys. Finally, simulations point the way forward. Better resolution, more complete physics, including improved semi-classical and quantum field models, and longer integration times will all sharpen predictions. Collaborations between numerical relativists, particle theorists, and observational astronomers are already beginning to translate simulated signatures into search templates for gravitational wave detectors and high-resolution interferometers. Even null results are useful, By simulating what wormholes would look like and then failing to detect those signatures, observers can place constraints on the abundance or parameter ranges of such exotic objects. The computational story, then, is a story of possibility and constraint. Simulations show that wormhole-like geometries can form in dynamic, engineered, or exotic matter scenarios. They show how throats might imprint distinctive light and gravitational wave signatures, and they show how fragile such configurations are when confronted with realistic physics. They neither guarantee nor forbid wormhole stars, but they transform the question from metaphysical musing into a concrete program of modeling and observational testing. If wormhole cores are to move from speculative curiosity to empirical science, simulations will be the bridge that connects bold theoretical ideas to measurable reality. Among the many exotic proposals for keeping wormholes open, one of the most fascinating involves cosmic strings, thin, one-dimensional defects in spacetime that might have formed in the very early universe. Cosmic strings are not strings in the everyday sense, but are closer to cracks in the cosmic fabric, regions where the universe failed to fully smooth out during phase transitions in its earliest fractions of a second. If they exist, they would be unimaginably dense. A single cosmic string thinner than a proton could outweigh a mountain, and their gravitational influence would be extreme despite their vanishingly small width. The connection to wormholes arises from the unique way cosmic strings warp spacetime. A straight cosmic string creates a conical geometry. Space around it is flat, but with a missing angle, as though a wedge has been cut out and the edges stitched together. This produces unusual lensing effects and peculiar gravitational forces. Some theorists have speculated that if a cosmic string were to thread through the throat of a wormhole, its intense tension could counteract the collapse that normally dooms such structures. In effect, the string could act as a stabilizing scaffold, holding the tunnel open by its own extreme energy density. There are variations on this idea. Some models suggest two cosmic strings, passing close to each other or connected in loops, could frame a wormhole entrance, locking its geometry in place. Others invoke cosmic string networks, remnants of the early universe's symmetry breaking, as potential cosmic engineering tools that naturally generate stable wormhole structures. These are speculative to the extreme, since we have not confirmed cosmic strings themselves, but the mathematics does not forbid the possibility. In parallel, there are proposals that quantum effects themselves could stabilize wormholes, even without strings. Quantum field theory allows for negative energy densities in very specific, localized situations, such as the Casimir effect, where two metal plates placed extremely close together in a vacuum experience an attractive force because the quantum fluctuations between them are restricted. If such negative energy can exist in the lab, then perhaps in the wild, on cosmic scales, quantum fields could provide the repulsion needed to counteract gravitational collapse at a wormhole throat. In some models, a constant interplay of quantum fluctuations creates just enough pressure to keep the tunnel from snapping shut. The cosmic string and quantum stabilization hypotheses share a common trait. They take physics that might plausibly exist, topological defects or quantum effects, and stretch them to their cosmic limits. Neither requires rewriting the laws of nature entirely, though both involve phenomena we have never directly observed. If either proves true, wormholes wouldn't demand entirely magical forms of matter. Instead, they could emerge as natural consequences of the universe's own structure. If wormhole stars are real, some might be pinned open by cosmic strings threading through their cores, invisible to us but exerting their stabilizing influence nonetheless. Others might flicker in and out of stability as quantum effects play tug-of-war with gravity. Both ideas extend the range of possibilities, reminding us that the universe often reveals creativity that surpasses human imagination. When we step back and think about the practical implications of wormhole stars, one of the most exhilarating possibilities comes into focus. They could serve as galactic gateways, natural shortcuts through the cosmos. Space is vast on a scale that defies comprehension. Even at light speed, it would take over 4 years to reach the nearest star beyond our Sun, and tens of thousands of years to cross our galaxy. Traveling between galaxies is almost unthinkable, millions of years, even at the ultimate speed limit. Against this backdrop, the idea of a star harboring a wormhole core is electrifying. Such an object wouldn't just be a curiosity of physics, it could be a cosmic bridge, turning journeys of millions of years into steps across a threshold. The basic idea is simple in concept but staggering in its implications. If certain stars, perhaps mistaken for black holes or exotic remnants, are actually wormholes, then entering their gravitational field could deliver you elsewhere, maybe across the galaxy, maybe across intergalactic space. Imagine a spacecraft orbiting such a star, probing its behavior, and then plunging into the core. Instead of being crushed in an inescapable singularity, the ship passes through the wormhole throat and emerges light years, perhaps even millions of light years, away. To observers outside, it would appear as though the ship vanished at one star and mysteriously reappeared near another. Galactic gateways solve one of the most profound problems in interstellar travel: distance. Even the most optimistic propulsion technologies, fusion drives, antimatter rockets, or solar sails, struggle against the sheer immensity of space. Wormhole stars, by contrast, would bypass the need for travel in the usual sense. They wouldn't just make exploration faster, they would redefine what distance means, collapsing the galaxy into a network of nodes connected by invisible tunnels. Entire civilizations could be built not around planets or solar systems, but around wormhole stars, the hubs of a cosmic transportation grid. Of course, such gateways wouldn't be trivial to use. Their gravitational fields would be hazardous, requiring precision navigation to avoid destruction. The stability problem would loom large. If the wormhole throat were unstable, a ship entering might be torn apart as the passage collapsed. Exotic radiation leaking from the core could pose additional dangers. But if advanced civilizations learn to predict, stabilize, or even harness these stars, then galactic travel could shift from fantasy to practical reality. The gateway vision also raises questions about natural distribution. Are wormhole stars rare flukes, isolated oddities scattered randomly? Or could they be clustered, perhaps forming natural networks where cosmic strings, exotic matter, or specific collapse processes are more common? If so, then there might already be hidden highways across the universe, waiting to be discovered. To us, they would appear as unusual black hole candidates, but to a civilization advanced enough to recognize and exploit them, they would be the backbone of intergalactic expansion. And consider the tantalizing possibility that wormhole stars might already be used by others. If extraterrestrial civilizations exist, and if even one of them has learned to identify and navigate wormhole gateways, their presence in our galaxy could be far more extensive than we realize. Travel times between distant regions would shrink to hours or days. Colonies could be maintained across vast stretches of space with ease. The idea of galactic empires, so common in science fiction, suddenly gains a real physical foundation. Wormhole stars as galactic gateways also offer a poetic symmetry. Stars, the traditional anchors of cosmic navigation, would become not just waypoints but actual portals. For ancient human explorers, stars were guides across oceans. For future explorers, wormhole stars might be guides across galaxies, lighthouses marking entrances to hidden pathways in space-time. The universe is a labyrinth of unimaginable distances, but if even a handful of stars conceal wormhole cores, the labyrinth might already contain doors. We may simply not have learned how to find the keys yet. If the notion of wormhole stars as shortcuts across the galaxy feels staggering, then expanding that vision to include parallel universes takes us into an even deeper frontier. The equations of general relativity don't restrict wormholes to connecting 2 points within the same universe. Instead, they leave open the possibility that a wormhole could serve as a bridge between entirely separate universes, different spacetimes, perhaps with their own physical constants, histories, and even dimensions. If this is true, then some stars could be far more than galactic gateways. They could be doorways into other realities altogether. The idea of parallel universes, or the multiverse, has its roots in both physics and philosophy. Quantum mechanics suggests that reality is not singular but spread out across possibilities. Inflationary cosmology, which describes the rapid expansion of the universe after the Big Bang, implies that different regions of spacetime could inflate into separate bubble universes, each cut off from the others by vast expanses of cosmic inflation. If wormholes exist, they could act as tunnels between these bubbles, circumventing the isolation that otherwise seems absolute. In that sense, wormhole cores inside stars might not just relocate matter across our galaxy but deliver it into an entirely foreign cosmos. Now imagine what this would mean for exploration. A civilization entering a wormhole star might not emerge in some distant corner of the Milky Way, but in a universe where the laws of physics themselves are subtly, or dramatically, different. The strength of gravity could vary, altering the very structure of galaxies. The speed of light might change, reshaping causality. Chemistry could follow new rules, leading to alien forms of matter and life unimaginable to us. A star that hides a wormhole core would not just be a portal through space, but a gateway into the ultimate unknown. The possibility also reframes the mystery of black holes. When matter falls into a black hole, we assume it's destroyed or compressed into a singularity. But if black holes are secretly entrances to wormholes, then perhaps the matter is not destroyed at all, it is transferred elsewhere. To us, it disappears into the void. In another universe, it might suddenly appear as a white hole, spewing out energy and particles into a cosmos that has never known us. Our black holes could be their fountains of creation. From a philosophical angle, this raises haunting questions. Are wormhole stars responsible for seeding other universes with matter? Could our own universe have been born from the outflow of a white hole in a parent cosmos? If so, then wormholes are not just bridges between universes, they are part of the machinery of cosmic evolution, with stars as midwives delivering matter across the boundaries of existence. Even in scientific speculation, the possibility of multiverse-connected wormholes is taken seriously enough to appear in advanced theoretical discussions. Models of quantum gravity, string theory, and loop quantum cosmology sometimes predict that space-time is not a sealed container but part of a larger fabric where multiple universes coexist. Wormholes become the seams or stitches in that fabric. Stars with wormhole cores could thus be the physical markers of these hidden interconnections. The observational consequences of such parallel universe connections are harder to imagine, but not impossible. A wormhole star that links to another universe might exhibit energy leaks or radiation signatures that don't fit any known process. It could appear to bleed energy from nowhere or eject particles that don't match our particle physics. Astronomers might already be staring at such anomalies without realizing their significance. What looks like a strange quasar or a mysterious gamma-ray burst might, in fact, be a star acting as a doorway into another cosmos. To think of stars as cosmic gateways is awe-inspiring. To think of them as bridges into other universes is humbling. It transforms the night sky into something far grander, not just a map of our galaxy but a network of possible roads into realities we cannot yet imagine. If wormhole stars exist and connect to parallel universes, then the stars above us may be more than light from afar, they may be invitations. The multiverse is one of the most daring and controversial concepts in modern science. It suggests that what we call the universe may not be the whole of reality, but merely one bubble in a vast cosmic ocean. Instead of a singular, self-contained cosmos, there may be countless universes, each with its own set of physical laws, constants, histories, and possibilities. And if wormhole stars exist, they might not only confirm this idea but also provide physical doors between these alternate realities. There are several versions of the multiverse theory, each born from different branches of physics. The cosmological multiverse arises from the theory of cosmic inflation. In the first instant after the Big Bang, space-time is believed to have expanded exponentially fast, like a balloon inflating. Inflation may not have ended everywhere at once, creating isolated pockets or bubbles of space-time. Each bubble evolves into its own universe, cut off from others by vast regions of inflating space. Our universe is just one such bubble. In this view, wormholes might act like tunnels punched through the barriers of cosmic inflation, linking two otherwise disconnected bubble universes. A star with a wormhole core would then serve as an inter-bubble doorway, something like a hidden bridge across the multiversal sea. Another approach comes from quantum mechanics, particularly the many-worlds interpretation. According to this framework, every quantum event doesn't collapse into a single outcome but instead spawns new universes for every possibility. If this interpretation reflects physical reality, then countless versions of us exist across parallel universes, each branching with every decision and quantum fluctuation. Wormhole stars, in this context, might be shortcuts not just to distant places but to alternate timelines, other realities where history unfolded differently. Passing through such a star could mean entering a world where Earth developed differently, civilizations evolved along new paths, or entirely alien versions of nature prevailed. There's also the string theory landscape, which predicts an enormous variety of possible universes, each with different configurations of extra dimensions and physical constants. In that view, the multiverse is not just possible but inevitable. Wormholes, embedded within certain stars, could function as tunnels through the higher dimensional structure that connects these universes. To beings in our three-dimensional space, such wormhole stars would appear as bizarre, powerful objects. In the broader landscape, they would simply be doorways threaded through extra dimensions. The most radical idea is that wormhole stars could act as selective portals into the multiverse. Unlike ordinary stars, whose role is to burn fuel and radiate light, these special stars would have a second purpose, acting as natural transition points between realities. Imagine our universe as a vast city, each universe as a building, and wormhole stars as hidden doors in those buildings that let you cross into a neighboring structure. If even one such star exists in our galaxy, it would be more than just an astrophysical curiosity. It would prove that our universe is not alone, that there are next-door neighbors separated not by distance but by reality itself. The implications are breathtaking. If wormhole stars truly connect to the multiverse, then they may explain mysteries we already observe. Strange bursts of radiation or unaccountable cosmic anomalies could be the leakage of energy from one universe into another. The unexplained balance of matter and antimatter in our universe could be the result of exchanges through multiversal channels. And the deep philosophical question of why our universe is so finely tuned for life might find an answer. Perhaps it isn't unique. Perhaps we live in one of countless universes, and wormhole stars are the rare cracks where their walls touch. But perhaps the most profound aspect of the multiverse angle is not scientific but existential. If wormhole stars are gateways, then they represent the ultimate frontier of exploration, not just traveling to distant stars or galaxies, but leaving our entire universe behind. What lies beyond could be familiar, strange, terrifying, or even incomprehensible. Yet the stars that dot our night sky might not simply be suns in the darkness. Some might be doors, glowing invitations to step beyond the boundaries of our reality and into the vastness of the multiverse itself. If wormhole stars really exist, then their most mind-bending implication may not be crossing galaxies or even universes, but crossing time itself. The idea that time travel could be possible through wormholes is one of those extraordinary predictions that arises naturally when you take Einstein's equations seriously. And it isn't just science fiction writers who have explored it. Serious physicists, from Kip Thorne to Stephen Hawking, have wrestled with the paradoxes and possibilities. If certain stars are hiding wormhole cores, they may also be hiding the keys to journeys not only across space, but across the past and future. The foundation of this concept lies in relativity. Time is not absolute, it bends, stretches, and warps depending on gravity and motion. A wormhole, being a tunnel through space-time itself, can be manipulated so that the two ends of the tunnel experience time differently. If one mouth of a wormhole is accelerated to near-light speed, or placed deep within a strong gravitational field, time at that end will pass more slowly relative to the other. This effect is not speculative. We observe time dilation regularly, in satellites orbiting Earth and in particle accelerators. Now, if the two ends of the wormhole are brought back together after experiencing different flows of time, a curious thing happens. Stepping through the wormhole connects you to a different temporal frame. In other words, you could enter the wormhole at one star and emerge not only in another place, but in another time. This leads to extraordinary possibilities. A civilization advanced enough to identify and stabilize a wormhole star could, in theory, construct a cosmic time machine. They could send probes or travelers through, emerging centuries in the past or future relative to their starting point. Wormhole stars would then become more than shortcuts through distance. They would be tunnels carved through the chronology of the universe. Entire epochs could be linked together by the throats of stars, allowing observers to witness the rise and fall of civilizations, or even revisit their own history. Of course, the paradoxes are immediate and profound. If wormhole stars allow backward time travel, then causality itself comes under threat. Could an explorer change history by traveling through such a star? Could a message sent into the past alter the future? These questions have haunted physicists as much as philosophers. Stephen Hawking even proposed the chronology protection conjecture, arguing that the laws of physics may conspire to prevent closed time loops from forming, perhaps by destabilizing the wormhole as soon as paradoxes threaten. In that case, wormhole stars might allow only forward travel, or might collapse when misused, shutting down the possibility of paradox. Still, the mathematics leaves the door tantalizingly ajar. Some researchers have shown that if exotic matter stabilizes a wormhole, nothing in relativity forbids using it for time travel. The problem is less about the math and more about the physics, whether exotic matter exists in sufficient quantity, whether wormhole throats can resist quantum instabilities, and whether the universe permits paradoxes at all. From an observational perspective, a wormhole star functioning as a time machine might betray itself in strange ways. Imagine a star emitting bursts of energy or matter that appear to come from nowhere, or appearing to anticipate events by releasing radiation patterns before they should logically occur. Some anomalies of this sort have puzzled astronomers already, though mainstream explanations usually lean toward pulsars, magnetars, or other exotic but non-time traveling sources. Yet if even one of these signals turned out to be from a wormhole star looping information back in time, it would redefine our understanding of reality overnight. The thought is dizzying. Above us in the night sky, some stars may be not just suns, not just gateways, but clocks with shortcuts built inside them, tunnels through which the river of time itself can be crossed. To find such a star would be to confront one of humanity's oldest dreams and deepest fears, the ability to step out of the present and into the pages of history, or the blank pages of tomorrow. The entire modern discussion of wormholes, wormhole stars, and their role as potential portals into space, time, or even parallel universes can be traced back to an elegant idea first proposed in the 1930s, the Einstein-Rosen bridge. This was the seed that planted wormholes in the imagination of physicists, and it remains a cornerstone in how we think about these mind-bending structures today. In 1935, Albert Einstein and his colleague Nathan Rosen set out to explore an odd feature of Einstein's own equations of general relativity. Black holes had not yet been observed, but the mathematics already hinted at their existence, regions where gravity becomes so intense that not even light can escape. Einstein and Rosen realized that if you extended the geometry of a black hole mathematically, something remarkable appeared. Instead of terminating at a singularity, a point of infinite density, the equations seemed to describe a tunnel connecting two distinct regions of space-time. They called this tunnel an Einstein-Rosen bridge. To visualize it, imagine space-time as a flat sheet. Normally, if you want to get from one point to another, you must travel across the sheet's surface. But if you fold the sheet and poke a hole through it, you create a shortcut. That shortcut is the bridge, a wormhole that connects distant regions. In principle, you could fall into one mouth of the wormhole and emerge elsewhere, bypassing the intervening space. The Einstein-Rosen bridge was revolutionary because it showed that wormholes weren't just science fiction fantasies. They naturally emerged from the mathematics of general relativity. However, there was a catch. The bridge Einstein and Rosen described was not traversable. It would collapse instantly if anything tried to pass through. This is because their bridge was essentially what we now recognize as the simplest kind of wormhole, one linking a black hole to a white hole. The throat of this wormhole pinches off so quickly that no particle, photon, or spaceship could survive the passage. Still, the concept was profound. It established that space-time is far more flexible and strange than common sense suggests. Einstein and Rosen weren't thinking of spaceships or time machines when they published their work. They were concerned with unifying gravity and electromagnetism. But their bridge became the foundation for later explorations. In the decades that followed, physicists like John Wheeler, Kip Thorne, and others would take the Einstein-Rosen bridge and ask, what if it could be stabilized? What if exotic matter could hold the throat open? What if, instead of collapsing, it could be a stable tunnel through which information and matter might pass? This is where wormhole stars re-enter the story. The idea that certain stars might conceal Einstein-Rosen bridges at their cores is a natural extension of that original insight. If the collapse of a star could generate the conditions for a black hole, then perhaps, under exotic circumstances, it could also generate a wormhole. In that case, the Einstein-Rosen bridge wouldn't just be a mathematical curiosity. It would be a real astrophysical object, a hidden feature of the universe, shining faintly or darkly in the night sky. And what makes this origin story even more poetic is that Einstein himself was skeptical of black holes. He disliked the idea of singularities, points where his equations broke down. In a way, the Einstein-Rosen bridge was his attempt to escape the singularity problem by imagining a smoother continuation of space-time. Ironically, decades later, wormholes would become associated with some of the most extreme singularities imaginable, black holes and the exotic stars that might mimic them. So when we talk today about wormhole cores in stars, or cosmic gateways to other universes, we are walking in the intellectual footsteps of Einstein and Rosen. Their bridge may not have been stable, but it opened a door in human thought, a bridge of ideas, if you will, that physicists and dreamers have been crossing ever since. Without it, the concept of wormhole stars might never have taken root. Despite the incredible elegance and excitement of wormhole theories, mainstream science approaches the idea of wormhole stars with profound skepticism. The reason is simple. While the mathematics allows for wormholes under certain conditions, nature has not provided any direct evidence that they exist. Most physicists view them not as physical objects in the night sky but as highly speculative constructs, useful for testing the limits of general relativity and quantum mechanics rather than objects likely to be discovered tomorrow. The skepticism begins with the issue of stability. As previously discussed, a traversable wormhole requires exotic matter or negative energy to counteract the inevitable gravitational collapse. We have no confirmed observations of such matter in nature. While quantum mechanics allows for negative energy densities in controlled, microscopic situations, like the Casimir effect, scaling these effects up to the size of a star is far beyond what we currently believe is physically plausible. Without exotic matter, the wormhole throat would pinch off almost instantly, rendering the structure completely inaccessible. This is not a minor technical hurdle. It is a fundamental obstacle that makes the existence of stable wormhole stars highly unlikely. There is also the problem of observational ambiguity. Many of the phenomena that might suggest a wormhole, unusual radiation patterns, gravitational lensing anomalies, energy leaks, or echoes in gravitational waves, can often be explained by more conventional astrophysical sources. Black holes, neutron stars, magnetars, quasars, and active galactic nuclei all produce extreme gravitational and electromagnetic environments that can mimic some of the hypothetical signals of wormhole stars. Disentangling a genuine wormhole signature from ordinary astrophysical noise is a daunting task, and to date, no data has unambiguously pointed toward a wormhole. Furthermore, the theoretical requirements for forming a wormhole within a star are extreme. Standard stellar evolution models do not predict the creation of wormhole cores. They predict black holes, neutron stars, or white dwarfs depending on the progenitor mass. The conditions under which a natural wormhole could emerge, precisely tuned distributions of exotic matter, perfectly symmetrical collapse, or the intervention of cosmic strings, are exceedingly rare and highly contrived. For many scientists, this makes the likelihood vanishingly small. Even the concept of wormholes connecting parallel universes or different points in time raises additional doubts. While the equations of general relativity allow such solutions, introducing time travel and multiverse connections generates paradoxes that may not be physically resolvable. Stephen Hawking's chronology protection conjecture suggests that the universe might have built-in mechanisms to prevent causal loops, essentially forbidding practical time travel through wormholes. If true, it would severely limit the functionality of any hypothetical wormhole star. Mainstream skepticism is also fueled by the lack of reproducible evidence. Unlike black holes or neutron stars, which have numerous observational confirmations, from gravitational wave detections to accretion disk imaging, wormhole stars remain purely theoretical. The absence of clear, repeatable signals consistent with wormhole behavior means that any claim of their existence is taken with extreme caution. Speculation is welcomed as a tool for theoretical exploration, but it is not a substitute for empirical validation. That said, skepticism does not equate to dismissal. The concept of wormhole stars pushes physicists to explore the boundaries of known physics, to model extreme geometries, and to test the interplay between general relativity and quantum theory. Many of the simulations, exotic star models, and stability analyses discussed earlier are performed precisely because, even if the objects themselves do not exist, they illuminate principles that might underlie quantum gravity, early universe cosmology, or black hole physics. Wormhole stars act as thought experiments with tangible mathematical foundations, challenging our understanding even if they remain undetected. In essence, wormhole stars occupy a liminal space in science. They are theoretically fascinating, mathematically consistent under certain assumptions, and astronomically alluring, yet empirically unverified. Mainstream scientists treat them as speculative, but useful, constructs. They are not outright forbidden by the laws of physics, but they are improbable given what we currently know. For this reason, discussions of wormhole stars often straddle the line between cutting-edge theoretical physics and imaginative extrapolation, blending rigorous mathematics with visionary hypotheses. One of the most promising avenues for settling the question of wormhole stars lies in the still unfinished quest for a theory of quantum gravity. While general relativity describes gravity and space-time curvature with extraordinary precision on macroscopic scales, it breaks down at singularities and in extreme conditions where quantum effects dominate. Conversely, quantum mechanics governs the microscopic world but struggles to incorporate the full influence of gravity. Wormhole cores, particularly those hypothetically residing inside exotic stars, exist precisely in the domain where these two frameworks clash: regions of intense gravity, extreme density, and potentially exotic matter. Until we develop a complete theory of quantum gravity, the existence of stable wormholes remains unresolved. Quantum gravity could play multiple roles in this question. First, it could clarify the true nature of singularities. Classical general relativity predicts that black holes culminate in a singularity, a point of infinite density where the laws of physics break down. However, a fully quantum description of gravity may replace these singularities with finite, non-divergent structures. If this is the case, then wormhole cores might naturally emerge as stable solutions within collapsing stars. The singularity would no longer be a destructive endpoint but a bridge connecting disparate regions of space-time. A theory of quantum gravity could tell us whether these bridges are fleeting mathematical curiosities or persistent physical entities. Second, quantum gravity would shed light on exotic matter and energy conditions. Traversable wormholes require negative energy density or matter with repulsive gravitational properties, something entirely absent in conventional matter. Quantum field theory suggests that negative energy can exist in limited, microscopic contexts, such as in the Casimir effect. But scaling this up to stellar or astronomical dimensions requires physics beyond the standard model. Quantum gravity might reveal mechanisms that generate sufficient negative energy naturally in collapsing stars or compact objects, stabilizing a wormhole throat for extended periods. This would convert wormhole stars from theoretical anomalies into plausible astrophysical entities. Third, quantum gravity could address the stability problem in a definitive way. Classical calculations predict that wormholes collapse instantly without exotic matter. But once quantum corrections are included, space-time itself may possess intrinsic elasticity, fluctuations, or topological features that counteract gravitational collapse. Certain approaches, such as loop quantum gravity or string-theoretic models, suggest that space-time may be granular or composed of interconnected structures at the Planck scale. These features could provide natural stabilization, allowing a wormhole throat to persist long enough to permit travel, or at least to leave detectable imprints on the surrounding environment. A fourth potential insight involves information transfer and black hole paradoxes. Wormholes have been invoked as possible resolutions to the black hole information paradox, the puzzle of whether information that falls into a black hole is destroyed, violating quantum mechanics, or somehow preserved. Quantum gravity may reveal that wormhole cores inside certain stars act as conduits, enabling information to escape into another region of space-time, a parallel universe, or even a distant time. This would unify the concepts of wormholes, black hole interiors, and quantum information in a single framework, showing that what appears destructive in classical relativity may actually be a bridge. Finally, a robust theory of quantum gravity could generate testable predictions. For instance, it might calculate specific radiation patterns, gravitational wave echoes, or high-energy particle emissions unique to wormhole cores, allowing astronomers to distinguish these stars from ordinary black holes or neutron stars. Right now, the distinction is largely speculative. With quantum gravity, we could move from thought experiments to observational science, designing telescopes and detectors to search for the fingerprints of wormhole stars. The role of quantum gravity is both constraining and liberating. On one hand, it could rule out wormhole cores entirely, showing that quantum effects prevent the formation of traversable tunnels, even in the presence of exotic matter. On the other hand, it could reveal new physics that makes wormhole stars not only possible but perhaps inevitable in certain extreme conditions. In either scenario, quantum gravity is the key. Without it, our speculation is limited to classical solutions and imaginative extrapolation. With it, wormhole stars become either a scientifically grounded possibility or a problem definitively solved by the deeper structure of reality. One of the most profound puzzles in modern physics is the black hole information paradox, and wormhole stars sit at the edge of this debate in a surprisingly natural way. The paradox arises from the clash between general relativity and quantum mechanics. Classical general relativity predicts that information falling into a black hole is irretrievably lost behind the event horizon, eventually swallowed by the singularity. Quantum mechanics, on the other hand, asserts that information cannot be destroyed. Every quantum state must evolve in a reversible, unitary fashion. Reconciling these conflicting principles has stumped physicists for decades, and wormhole stars offer a tantalizing, if speculative, avenue to address the problem. Consider the classic view of a black hole. An enormous concentration of mass collapses to a singularity, surrounded by an event horizon that traps everything inside. If a probe or particle falls in, all traces of its quantum information seem lost to the universe. Stephen Hawking formalized this problem in the 1970s, demonstrating that black holes emit radiation, now known as Hawking radiation, due to quantum effects near the horizon. This radiation is thermal, meaning it carries no detailed information about the matter that fell in. Over time, the black hole evaporates, leaving behind nothing but featureless radiation. Where, then, did the information go? Enter wormhole stars. If a star conceals a wormhole at its core instead of a classical singularity, the lost matter and information may not vanish at all. Instead, the information could be transmitted through the wormhole to another region of spacetime, or even to another universe entirely. In this scenario, what appears from the outside as a black hole swallowing matter would actually be a more complex and dynamic process. The matter, and its quantum information, is redirected rather than destroyed. The black hole information paradox, therefore, might be resolved not by modifying quantum mechanics or inventing new physics, but by recognizing that certain black holes are in fact wormhole stars, with their hidden throats serving as channels for information. Some theoretical frameworks make this more concrete. In the ER=EPR conjecture proposed by Juan Maldacena and Leonard Susskind, quantum entanglement, EPR pairs, and Einstein-Rosen bridges, ER bridges, or wormholes, are suggested to be fundamentally linked. In this view, entangled particles could be connected by microscopic wormholes, and large-scale wormhole cores in stars could be seen as macroscopic realizations of this principle. If matter falling into a black hole is entangled with something elsewhere, the wormhole could act as a conduit, preserving correlations that otherwise appear lost. This creates a framework where the universe obeys both general relativity and quantum mechanics, potentially resolving the paradox without violating either. Moreover, wormhole cores offer an alternative perspective on Hawking radiation itself. Normally, Hawking radiation is thought to be thermal and uninformative. But if the black hole is secretly a wormhole star, radiation might leak through the throat, carrying subtle imprints of the ingested matter. Observers outside might see energy escaping in seemingly random bursts, yet a sufficiently sensitive detector could, in principle, decode information about the original content. In this way, the star would appear to evaporate in accordance with Hawking's calculations while still maintaining unitarity, the preservation of quantum information. There are additional philosophical implications. If wormhole stars transmit information elsewhere, it reframes our understanding of black holes as cosmic endpoints. They are no longer absolute prisons but rather intricate hubs in a larger network of spacetime, potentially connected to other galaxies, other times, or even other universes. From this perspective, the apparent destruction of matter is an illusion born of our limited vantage point. The universe itself remains fundamentally conservative of information. Skeptics rightly caution that this remains speculative. The physics required, stabilized wormholes, exotic matter, consistent quantum gravity effects, has yet to be observed. But as a theoretical construct, wormhole stars provide a framework that naturally accommodates information preservation, linking two of the most challenging concepts in physics, black holes and quantum unitarity. They transform the paradox from an unsolvable conundrum into a potential bridge, a literal and conceptual passage for matter and information that may exist at the heart of the most extreme stars. One of the intriguing ways wormhole stars might reveal themselves is through unusual energy emissions, particularly phenomena related to Hawking radiation. In classical black hole theory, Hawking radiation is a subtle effect arising from quantum fluctuations near the event horizon. Particle-antiparticle pairs spontaneously pop into existence. One falls into the black hole, the other escapes, creating a faint thermal radiation that gradually drains the black hole's mass. The effect is extremely weak for stellar mass black holes, but it offers a tantalizing bridge between quantum mechanics and general relativity, a bridge that wormhole stars could manipulate in surprising ways. If a star harbors a wormhole core rather than a singularity, the dynamics of Hawking-like radiation could be drastically altered. Instead of the radiation being purely thermal and featureless, energy might leak through the wormhole throat. Some of the escaping radiation could carry subtle correlations with matter or energy that entered the wormhole, effectively encoding information that would otherwise seem lost. To an outside observer, the star might appear to emit bursts or fluctuations inconsistent with conventional black hole predictions, slightly brighter, more irregular, or displaying unexpected spectra. These anomalies could be one of the few observable signatures hinting at a hidden wormhole inside. The idea extends to energetic jets and particle emissions. Some black holes and neutron stars are known to produce intense, collimated jets of plasma moving at near-light speed. These are generally attributed to magnetic field interactions with the accretion disk, but wormhole cores could subtly influence the process. For instance, if a wormhole throat connects to a distant point in spacetime or another universe, matter spiraling into the star might encounter extreme tidal and geometric forces that redirect part of its energy through the throat, emerging as unusual radiation or high-energy particle streams. Such emissions would defy standard models, potentially revealing themselves as anomalies in X-ray, gamma-ray, or neutrino observations. Even small deviations in Hawking-like radiation could serve as clues. For conventional black holes, the emission spectrum is expected to be nearly perfect blackbody radiation, shaped only by the mass and spin of the black hole. A wormhole core, however, might produce irregularities in intensity or spectral shape, due to the complex geometry of the throat and the influence of exotic matter. In extreme cases, energy could be preferentially channeled along specific directions, creating hotspots or time-dependent flares that don't match any known astrophysical process. Observers with sensitive instruments might detect these anomalies as temporal or spectral echoes, pointing to physics beyond the ordinary. Some theoretical work even suggests that wormhole throats could act as energy amplifiers. When matter falls toward a wormhole core, tidal forces and interactions with the exotic matter inside could convert some gravitational potential energy into unusual forms of radiation. Unlike conventional accretion processes, where energy is radiated predominantly from a disk outside the event horizon, these emissions could originate from the deep interior, effectively leaking through the wormhole. This could produce energy patterns inconsistent with expectations for a black hole of comparable mass. It's important to emphasize that these effects would be subtle, and disentangling them from ordinary astrophysical processes is extremely challenging. Jets, flares, and gamma-ray bursts occur naturally in many compact objects. But in principle, precise measurements of radiation spectra, variability patterns, and high-energy particle emissions could reveal discrepancies that point toward the presence of a wormhole core. Advanced telescopes, space-based X-ray observatories, and neutrino detectors may someday be sensitive enough to capture these fingerprints. Hawking radiation, often considered a purely theoretical effect for distant black holes, becomes a potential diagnostic tool in the hunt for wormhole stars. Rather than being a faint whisper of quantum mechanics, it could carry encoded messages from the heart of these exotic objects. If astronomers detect energy leaks or radiation anomalies that cannot be reconciled with conventional models, it would provide the first hint that some stars are not ordinary. They may hide tunnels through space-time, linking distant regions, parallel universes, or even different epochs of time. If wormhole stars exist, then one of the most critical questions is how we could detect them among the countless ordinary stars and black holes in the cosmos. While these exotic stars might masquerade as black holes at first glance, their unique space-time structures would leave subtle, but potentially measurable, imprints on the light, radiation, and gravitational waves they interact with. Identifying these cosmic signatures is the first step in turning a theoretical curiosity into an observable astrophysical phenomenon. One of the clearest potential signatures is gravitational lensing anomalies. Massive objects bend the path of light, and black holes do so extremely. A wormhole star, however, could bend light in more complex ways. Light passing near a wormhole throat might be deflected in multiple directions, producing duplicated images, unusual magnifications, or even phantom images that have no corresponding visible source in normal space. Advanced telescopes using high-resolution imaging could detect these distortions, and deviations from expected black hole lensing patterns could provide hints of a hidden tunnel in space-time. Another signature could come from timing anomalies in accretion emissions. Many black holes are surrounded by accretion disks, and the infalling matter emits X-rays, gamma rays, and other high-energy radiation in regular or quasi-periodic patterns. If a wormhole core exists, matter spiraling toward the star could be partially diverted through the wormhole throat or experience irregular tidal forces. This could create subtle temporal fluctuations or echoes in the emitted radiation that differ from the smooth profiles expected around conventional black holes. Some theoretical studies even suggest that short, delayed bursts of light, gravitationally echoed through the wormhole geometry, could be a telltale sign. Gravitational waves offer another promising avenue. When compact objects like neutron stars or black holes merge, they create ripples in spacetime detectable by instruments like LIGO and Virgo. A merger involving a wormhole star might produce post-merger echoes or waveforms that differ from those predicted by classical black hole mergers. These deviations could be caused by matter reflecting off or interacting with the wormhole throat instead of being absorbed into a singularity. Detecting such deviations would require highly sensitive analysis, but gravitational wave astronomy is advancing rapidly, making this a real possibility in the near future. High-energy particle emissions could also betray a wormhole star. Some wormhole models predict that exotic particles or energy leaks might escape from the throat, producing neutrinos, gamma rays, or other forms of radiation that do not match standard astrophysical mechanisms. Observatories such as IceCube, the Cherenkov Telescope Array, and next-generation gamma-ray detectors could potentially detect these anomalous signals. The key would be distinguishing them from other cosmic sources. The spectrum, intensity, and temporal patterns would have to match predictions from wormhole models, rather than conventional stellar or black hole activity. The shadow of the star could offer another clue. The Event Horizon Telescope famously imaged the shadow of the supermassive black hole in M87. A wormhole star might produce a different shadow profile due to the way light bends around the throat. Instead of the nearly circular silhouette expected from a black hole, simulations suggest that wormhole cores could produce elongated, distorted, or even duplicated shadows, depending on the throat geometry and orientation relative to the observer. Future high-resolution imaging of compact objects could reveal such anomalies, potentially distinguishing wormhole stars from their black hole doppelgangers. Another subtle signature could arise from energy conservation anomalies. Infalling matter may seem to vanish from normal space but reappear elsewhere through the wormhole. If the process is imperfect, some energy could escape locally in unusual ways, leading to small but measurable deviations in the mass-to-energy conversion of the system. These deviations could manifest as unexplained brightening, unexpected radiation spikes, or shifts in the orbital dynamics of nearby objects, clues that a conventional black hole model cannot explain. Finally, wormhole stars might reveal themselves through multi-messenger correlations. By combining gravitational waves, electromagnetic radiation, and neutrino observations, astronomers could detect discrepancies that single-messenger studies would miss. For example, a gravitational wave signal from a merger might predict a particular timing and intensity of emitted light, but the observed electromagnetic signature could be delayed or modified due to interactions with a wormhole throat. Such inconsistencies would hint at a fundamentally different internal structure than that of a standard black hole. In essence, wormhole stars would not shout their presence but whisper it in subtle, complex ways. Light bending in unexpected directions, temporal echoes in high-energy emissions, anomalous gravitational wave patterns, unusual particle streams, and distorted shadows could all serve as cosmic fingerprints. By carefully analyzing these signatures, astronomers might separate these extraordinary objects from the vast sea of conventional stars and black holes, potentially turning a speculative theory into a testable branch of astrophysics. If wormhole stars exist, approaching one would be an exercise in both awe and extreme peril. These are not ordinary stars. They are objects of immense gravity, exotic matter, and potentially unstable geometry. Even with the most advanced spacecraft and technology, any attempt to get close would involve facing severe, life-threatening hazards that go far beyond what conventional space travelers encounter. The first and most obvious danger comes from gravitational tidal forces, often sensationalized as spaghettification. In the intense gravitational gradient near a wormhole star, the difference in gravitational pull between your head and your feet, or the front and rear of a spacecraft, would be enormous. Near the wormhole throat, these tidal forces could stretch and compress matter violently. Any human, ship, or probe venturing too close without proper shielding or countermeasures could be stretched into long, thin filaments, or crushed along certain axes. Unlike black holes, the geometry of a wormhole core could amplify these tidal stresses unpredictably due to its exotic space-time curvature, making safe navigation extremely difficult. Radiation is another critical hazard. Many of the high-energy processes that accompany massive stars or black holes, accretion of matter, jet emissions, or energy leaks from the wormhole throat itself, would expose an approaching spacecraft to lethal doses of X-rays, gamma rays, and energetic particles. If the wormhole connects to a distant region of space, the energy emerging from the throat could be completely unfamiliar, including bursts or pulses of radiation with spectra we have no experience shielding against. Without advanced deflection systems or energy-absorbing materials, exposure could destroy electronic systems, damage spacecraft hulls, or incapacitate biological occupants in seconds. The stability of the wormhole itself represents yet another existential risk. Traversable wormholes are highly sensitive to disturbances. Even small perturbations, an incoming asteroid, a sudden influx of matter, or interactions with the spacecraft itself, could trigger catastrophic collapse. If the throat closes while an object is passing through, the consequences could be instant and violent. The object would be crushed or torn apart by extreme space-time curvature. Unlike black holes, where crossing the event horizon has predictable outcomes, wormhole stars introduce uncertainty because the throat may behave dynamically, oscillating, pulsing, or even collapsing sporadically. The gravitational environment around a wormhole star may also be highly asymmetric. Exotic matter distributions, the influence of cosmic strings, or interactions with the surrounding galactic environment could produce unpredictable accelerations or gravitational anomalies. A spacecraft attempting to maintain a stable orbit might find itself suddenly flung into extreme trajectories, potentially colliding with the star, falling into the throat unexpectedly, or being ejected at relativistic speeds. Pilots or automated navigation systems would need to calculate and adapt to forces beyond any conventional celestial mechanics. Additionally, unknown physical phenomena may lurk near the throat. If the star connects to another universe or a distant region of space-time, the inflow and outflow of energy could be irregular and extreme. Exotic particles or bursts of energy could interfere with instruments or destabilize the spacecraft's trajectory. Even minor mistakes in approach could expose explorers to unpredictable forces, including gravitational shock waves or time dilation effects that distort the perception of events and decision-making. Finally, there is the psychological and operational risk. If a wormhole star allows for time travel or connection to parallel universes, the very passage through it could alter temporal flow relative to the home system. An explorer might emerge seconds, years, or centuries later, disoriented and stranded in a region of space, or reality, they do not recognize. The uncertainty of exit conditions makes planning and survival extraordinarily difficult. In short, approaching a wormhole star would combine the most extreme hazards known in astrophysics: spaghettifying tidal forces, lethal radiation, unstable space-time geometry, unpredictable gravitational anomalies, and temporal uncertainty. Only civilizations capable of mastering advanced shielding, navigation, and energy management, even perhaps control over exotic matter itself, could attempt such a venture with any reasonable expectation of survival. For now, the dangers reinforce why wormhole stars remain purely theoretical and why, even if they exist, they may remain cosmic mysteries rather than destinations. The quest to identify wormhole stars, or at least rule out their existence, may hinge on the next generation of astronomical observatories. Current instruments, while extraordinarily advanced, are limited in their ability to detect the subtle anomalies that could differentiate a wormhole star from a conventional black hole, neutron star, or exotic stellar remnant. However, upcoming telescopes and multi-messenger observatories promise unprecedented sensitivity across the electromagnetic spectrum, as well as in gravitational waves and high-energy particles, potentially opening a window into these extraordinary objects. One major leap will come from next-generation X-ray and gamma-ray observatories. High-energy emissions are a hallmark of compact objects, especially those involving accretion disks and strong gravitational fields. Wormhole stars, if they exist, may produce unusual X-ray or gamma-ray signatures due to matter interacting with exotic matter inside the throat, or energy leaking unpredictably through the wormhole. Instruments like Athena, Advanced Telescope for High-Energy Astrophysics, and EXTP, Enhanced X-ray Timing and Polarimetry Mission, are designed to provide far greater sensitivity and temporal resolution than current observatories. These telescopes could detect subtle deviations in the timing, spectrum, or polarization of X-rays from candidate wormhole stars, allowing astronomers to identify anomalies incompatible with conventional black hole physics. Another promising avenue lies in gravitational wave astronomy. LIGO and Virgo have already revolutionized our understanding of black hole mergers, detecting ripples in spacetime from events billions of light-years away. Future detectors like LISA, Laser Interferometer Space Antenna, scheduled to launch in the 2030s, will operate in the low-frequency gravitational wave regime, opening access to signals from supermassive compact objects. Wormhole stars involved in mergers could produce echoes or waveform distortions distinct from ordinary black hole interactions. LISA's sensitivity to these effects might allow scientists to detect the subtle imprints of a wormhole throat, giving indirect evidence for their existence. In addition, radio telescopes and interferometric arrays, like the next phases of the Square Kilometre Array, SKA, will dramatically enhance our ability to map gravitational lensing effects. Wormhole stars are expected to bend light in unusual ways, potentially producing duplicated images, lensing anomalies, or strange shadow shapes. High-resolution radio observations could reveal these subtle distortions in the light of background stars or galaxies, providing one of the clearest observational fingerprints of a wormhole core. Neutrino observatories also offer an exciting opportunity. If wormhole stars emit high-energy neutrinos through exotic interactions in the throat, next-generation detectors like IceCube Gen 2 could capture these elusive particles. Unlike photons, neutrinos pass through matter virtually unimpeded, carrying information from deep within the star that would otherwise be inaccessible. Detecting unexpected neutrino fluxes coinciding with other anomalous signatures could provide strong indirect evidence of exotic stellar cores. Space-based observatories focused on multi-messenger astronomy will be especially valuable. The combination of electromagnetic signals, gravitational waves, and neutrino observations allows scientists to cross-verify anomalies and reduce false positives. For instance, a star exhibiting unusual X-ray variability, gravitational wave echoes, and correlated neutrino emissions could become a prime candidate for a wormhole star, even if each signal individually could be explained by more mundane phenomena. Coordinated observations will enable more precise modeling and reduce uncertainty in interpreting subtle deviations from conventional astrophysics. Finally, the growing capabilities in high-resolution imaging, like the techniques that produced the first image of a black hole's shadow in M87, may eventually allow direct observation of wormhole throat geometry. Future enhancements in imaging resolution and computational reconstruction could reveal distorted or duplicated shadows, light-bending anomalies, or dynamic structures inconsistent with a simple black hole. This would provide the most direct visual evidence of a wormhole core, confirming one of the most radical predictions of modern theoretical physics. In essence, the tools to investigate wormhole stars are on the horizon. These observatories will not only allow us to detect potential wormhole signatures but also constrain theories, guiding physicists toward understanding whether these objects are real or remain a beautiful mathematical abstraction. If wormhole stars exist, the coming decades may be the first time humanity can probe them empirically, transforming speculation into tangible science. If wormhole stars exist and are stable enough to navigate, the implications for an advanced civilization are nothing short of staggering. These exotic stars could function as cosmic highways, natural hubs of interstellar or even intergalactic travel, reducing journeys that would otherwise take millennia to mere hours or days. The theoretical concept of navigating such objects requires imagining technologies far beyond our current capabilities, yet physics provides a framework in which such voyages might be possible. The first requirement for navigation would be precise gravitational mapping. Unlike ordinary stars or black holes, wormhole stars would warp spacetime in complex ways. An advanced civilization would need instruments capable of measuring not just the gravitational pull but the full three-dimensional geometry of the wormhole throat and its surroundings. With detailed maps, they could plot safe trajectories that minimize exposure to tidal forces, radiation, and instabilities. The civilization would essentially be piloting through a cosmic obstacle course, relying on real-time calculations and adaptive control systems to traverse the wormhole without being destroyed. Next would be the stabilization and modulation of the wormhole throat. Traversable wormholes are predicted to require exotic matter or negative energy to remain open. An advanced civilization might have discovered methods to enhance or stabilize the wormhole using controlled energy fields or exotic matter injections, effectively converting a naturally unstable structure into a reliable transport channel. This could also allow them to adjust the exit point, selecting which region of the galaxy, universe, or even point in time they emerge into. In theory, a civilization could maintain a network of stabilized wormhole stars, each functioning as a controllable gateway for ships, probes, or even information. Energy shielding and radiation management would be essential. Wormhole throats could emit unpredictable radiation, exotic particles, or bursts of gravitational energy. Sophisticated shielding technologies, perhaps based on advanced electromagnetic or gravitational field manipulation, would be necessary to protect vessels and inhabitants. Navigation systems might also need to anticipate and compensate for radiation-induced distortions of instruments or communications, allowing safe transit even under extreme conditions. The logistical possibilities are vast. A civilization with mastery over wormhole stars could colonize distant regions of their galaxy or even multiple galaxies. Supply chains could span light years with minimal delay, scientific cooperation could occur across cosmic distances, and strategic positioning of wormhole nodes could transform the civilization's spatial footprint. Instead of being confined to planets or solar systems, their infrastructure would be built around wormhole hubs, creating a lattice of travel routes that connect the galaxy like an interstellar subway system. Wormhole stars could also facilitate temporal and parallel universe exploration, assuming the cores connect to other points in time or alternative realities. An advanced civilization might study the past of their own universe, observe alternate histories, or conduct experiments in parallel universes without risking their home environment. This would require extreme caution, as even minor errors could have unpredictable consequences for causality, temporal continuity, or multiversal interactions. Nonetheless, the ability to access different times or realities would provide unparalleled opportunities for knowledge and expansion. Communication networks could likewise be revolutionized. If wormhole stars allow for instantaneous or near-instantaneous travel of signals, information could flow across vast distances in ways previously impossible. A civilization could maintain real-time contact between star systems separated by thousands of light-years, fundamentally changing the pace of culture, science, and governance. The galaxy would no longer be a collection of isolated systems but an interconnected web of knowledge and activity. The societal and philosophical impact of mastering wormhole navigation would be profound. The cosmos, once seen as an insurmountable expanse, becomes navigable and even familiar. Civilizations might orient themselves not around planets, stars, or galaxies, but around wormhole stars, the literal gateways to opportunity, exploration, and survival. Cultural and scientific paradigms would evolve to treat these stars not as distant curiosities but as essential infrastructure, central to commerce, diplomacy, and exploration. Yet the risks remain. Miscalculations, misalignments, or structural instabilities in the wormhole could be catastrophic. Even for a highly advanced civilization, traversing these stars would require vigilance, precision, and perhaps a profound understanding of the exotic physics governing their cores. But for those capable of mastering these challenges, wormhole stars would offer access to realms that are currently beyond imagination. Other galaxies, distant epochs, and perhaps even parallel universes. In essence, wormhole stars, if navigable, are not merely natural phenomena. They are tools of civilization, cosmic gateways that could redefine travel, exploration, and existence itself. The vision of a civilization hopping from one wormhole star to another transforms the night sky from a static landscape into a vast network of interconnected opportunities, each point of light potentially marking a door to the farthest reaches of reality. While wormhole stars remain hypothetical, certain unusual astronomical observations have fueled speculation that some stars or compact objects might host exotic structures reminiscent of wormholes. These observations often involve phenomena that challenge conventional explanations, from anomalous radiation to unexpected gravitational behavior. While none provide definitive proof, they offer tantalizing hints that something extraordinary could be occurring. One area of interest lies in rapidly fluctuating X-ray and gamma-ray sources. Astronomers have observed compact objects whose high-energy emissions vary in ways that do not conform to standard models of black hole or neutron star accretion. For example, some X-ray binaries display irregular bursts or flickering patterns that cannot be fully explained by disk instabilities or magnetic field interactions. In theory, a wormhole core could create localized gravitational anomalies that affect matter inflow, producing irregular emission patterns. Some researchers have speculated that these bursts could be signatures of energy leaking through a wormhole throat, though alternative explanations remain more conventional. Unusual gravitational lensing events have also sparked curiosity. Normally, massive objects bend light predictably, producing Einstein rings or multiple images of background sources. However, some observed lensing patterns deviate slightly from theoretical expectations. These deviations could, in principle, result from a wormhole's non-standard spacetime curvature, which might bend light in ways that differ from ordinary black holes or massive stars. While these anomalies are rare and subtle, they have prompted theorists to consider wormhole models as one possible explanation. Another intriguing observation comes from the study of so-called fast radio bursts, FRBs. FRBs are extremely brief, intense flashes of radio waves from distant galaxies. Their origins remain largely mysterious. Some speculative models suggest that if a compact star harbors a wormhole, interactions of matter or radiation with the throat could generate extremely short, high-energy pulses, potentially contributing to the observed FRB phenomena. While conventional astrophysical explanations, such as magnetar activity, remain more widely accepted, the sheer unpredictability and intensity of some FRBs make them consistent with exotic theoretical models. Gamma-ray bursts, GRBs, particularly short-duration bursts, have also drawn attention. GRBs are usually attributed to massive stellar collapses or neutron star mergers. Yet certain bursts exhibit peculiar energy distributions or delayed secondary flares that do not perfectly fit standard models. Wormhole cores could, in theory, redirect or release energy in ways that create these irregularities. While this remains highly speculative, the anomalies are sufficient to keep wormhole stars on the radar of theorists examining extreme cosmic events. High-resolution imaging of black hole shadows provides another indirect line of inquiry. Observations of the supermassive black hole in M87 and Sagittarius A reveal the silhouette of light bending around intense gravity. Some theoretical work suggests that if a wormhole core exists instead of a traditional singularity, the shadow might appear subtly distorted or elongated, depending on the orientation of the throat. Although current imaging lacks the resolution to detect these deviations definitively, future improvements could reveal shadow anomalies that hint at exotic structures rather than conventional black holes. Finally, unusual stellar motion and orbital behavior in densely packed galactic cores have sometimes defied conventional modeling. Stars orbiting what appear to be black holes occasionally show minor deviations from predicted paths. While dark matter, multiple body interactions, or unseen companions are more conventional explanations, some theorists suggest that non-standard gravitational fields, such as those produced by a wormhole core, could influence stellar dynamics in subtle but detectable ways. It is important to emphasize that all these observations are consistent with conventional astrophysics. Wormhole explanations are highly speculative and not widely accepted in the mainstream. Nonetheless, these anomalies serve a critical purpose. They provide test cases for theories, forcing astrophysicists to explore extreme geometries, exotic matter effects, and the limits of general relativity. Each unusual burst, lensing pattern, or orbital deviation is a potential clue, however tentative, that inspires continued theoretical investigation. The exciting prospect is that as observational technology improves, through more sensitive gravitational wave detectors, higher resolution telescopes, and multi-messenger astronomy, we may begin to identify patterns that cannot be reconciled with ordinary stars or black holes. While no observation to date has confirmed a wormhole star, these tantalizing anomalies keep the concept alive in the realm of theoretical astrophysics and encourage the careful scrutiny of data for signals that might hint at the extraordinary. If stars truly are portals to other universes, the philosophical implications would be staggering, reshaping not only science but our entire understanding of existence, reality, and humanity's place in the cosmos. Humanity has always looked at the night sky and felt both awe and insignificance. Stars have been symbols of constancy, guidance, and inspiration. To discover that some of them are doorways to entirely different realms would transform those symbols into literal pathways to the unknown. First, consider the implications for our understanding of reality itself. Modern physics has already challenged classical notions of space, time, and matter, but wormhole stars would take this to a new level. The universe we perceive as fixed and singular might instead be one among countless realities. Each wormhole star could connect not merely distant regions of our universe, but entirely separate universes, each with its own laws of physics, history, and forms of matter. Our perception of a singular cosmos would collapse, replaced by a multiversal tapestry, where reality is layered, interconnected, and far stranger than our senses can intuitively grasp. The discovery would also challenge philosophical assumptions about causality and determinism. If wormhole cores allow travel across time or into parallel realities, the cause and effect relationships we take for granted could be violated, or at least need profound reinterpretation. Actions taken near or within a wormhole star might ripple across time or across universes, forcing humanity to rethink notions of responsibility, free will, and consequence. Philosophers would have to grapple with scenarios in which decisions are not just local but cosmically entangled, affecting regions or realities far beyond our immediate experience. The existential implications would be equally profound. For centuries, humans have pondered the uniqueness of our universe and our place within it. The existence of wormhole stars would suggest that life, civilization, and perhaps consciousness could exist in other universes, fundamentally altering our sense of cosmic solitude. We would no longer be confined to speculating about distant planets in our own universe. The stars themselves could provide conduits to realms where completely different forms of life, intelligence, and even physics prevail. This could inspire both humility and a radical expansion of imagination, forcing humanity to consider its identity not in isolation, but as part of a far broader multiversal community. Furthermore, wormhole stars would transform our understanding of death and permanence. Traditional cosmology suggests that stars are born, live, and die according to predictable laws. If some stars are gateways, however, they might offer paths beyond ordinary mortality, passages to alternate realities, epochs, or universes where events unfold differently. The very concept of cosmic finality would be challenged. The death of a star might not be an end but a transformation, a window into a continuum far larger than our observable cosmos. Culturally, the discovery of such stars could redefine exploration and ambition. Humanity has always sent explorers to seas, lands, and planets. Wormhole stars would be the ultimate frontier. They would not just be points of light to chart, but actual portals to entirely new worlds. The night sky would become a map of infinite potential, each star a choice, a doorway, a challenge to our courage and ingenuity. The psychological impact of knowing that the universe is not bounded, that the impossible might be accessible, could inspire unprecedented advances in science, philosophy, and art. There would also be profound questions about ethics and risk. If wormhole stars connect to other universes or times, interventions could have consequences we cannot predict or control. The responsibility of exploration would escalate to a cosmic scale. One small action could affect an entire universe or timeline. Philosophy, ethics, and law might have to evolve to account for interuniversal consequences, creating frameworks that currently exist only in speculative fiction. Finally, the discovery of wormhole stars would bridge the gap between science and imagination. Human curiosity has always oscillated between what is known and what is dreamed. If the stars themselves are portals, the line between reality and possibility blurs. What once seemed like metaphysical speculation, parallel worlds, time travel, alternate realities, would gain empirical footing, transforming our worldview. We would confront a universe far more wondrous, terrifying, and exhilarating than we ever imagined, where science opens doors that philosophy had only dared to imagine. In short, wormhole stars would not just expand our understanding of physics, they would expand our understanding of existence, morality, identity, and the very fabric of reality. Humanity would have to reconsider its place in the cosmos not merely as observers, but as participants in an interconnected multiverse. Each star could be a doorway, each observation a choice, and each voyage a step into the infinite. As we reach the edge of this cosmic journey, it's impossible not to feel a mixture of awe, fear, and curiosity. Wormhole stars, if they exist, represent the ultimate convergence of science, imagination, and possibility. They could be gateways across space, time, and perhaps even reality itself, hiding behind the familiar glow of distant suns. They challenge every assumption we make about the universe, its size, its structure, the permanence of matter, and even the flow of time. They push the boundaries of what physics can explain and what humanity can hope to achieve. Yet, despite the mathematics, simulations, and tantalizing anomalies, these objects remain deeply mysterious. No telescope has yet definitively identified a wormhole star. No signal has been conclusively traced to a hidden throat linking one region of space to another universe or era. The idea exists today as a fascinating blend of theory, observation, and speculation, an intellectual frontier as daunting as it is alluring. And this uncertainty is part of their power. They force us to confront questions far larger than ourselves, questions about exploration, survival, and the very nature of existence. We can imagine the unimaginable, vessels navigating extreme gravitational fields, braving tidal forces that would tear apart ordinary matter, and passing through a throat that might deposit them across galaxies or into entirely alien realities. We can model the energy flows, simulate the exotic matter, and calculate the theoretical risks. We can even hypothesize about civilizations that have already mastered these cosmic highways, turning wormhole stars into tools for interstellar or interuniversal travel. But imagining is one thing, confronting the reality of such a star is another. The dangers are profound: spaghettification, lethal radiation, unstable collapse, and the unpredictability of traversing a bridge through space-time itself. And yet, for all the risks, the promise is breathtaking. The potential to travel instantaneously across light years, to glimpse alternate realities, or to unlock the secrets of time and the multiverse is the kind of possibility that has driven humanity to explore the unknown since the first fires were lit, the first oceans crossed, and the first stars charted. Wormhole stars are the ultimate frontier, simultaneously a scientific hypothesis and a philosophical mirror, reflecting our deepest curiosity and our capacity for courage. So, as we peer into the cosmos, scanning the heavens for unusual radiation, gravitational echoes, or lensing anomalies, we are confronted with a single, profound question. If wormhole stars exist, will we ever be brave enough to enter one? Will humanity possess the knowledge, technology, and daring required to step through the cosmic threshold and confront the universe, or multiverse, beyond? Perhaps the answer lies not just in physics, but in our willingness to embrace the unknown, to confront the terrifying and the wondrous alike, and to accept that the stars we see may be more than they appear, silent sentinels guarding pathways to the unimaginable. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.